Hi everyone, how are you all? Okay, so I hope all of you are doing great, right? So let's get started. Let me know if audio and video everything is fine. Let me know if everything is fine, and then we will start, right? Okay, okay. So I think everything is fine, right? Can you just confirm if there is any issue or everything is fine, so that we can start. Okay, okay. Hi Shivam. Hi Mohit. Hello Anupam. So today we are going to solve some recurrence relation, and we will start from very basic, which means there won't be any assumption that I will be doing that. Okay, you already know some of the things or you don't know some of the things. So we will be starting with very basic and to advance, and then we will be solving all the PYQs also. Okay, so most of the tricky PYQs we will be solving here only. So let's get started. Cool. Now let's just start. So the topic is that we want to solve the recurrence relations, right? Now, for example, this particular program is given to you. Now, can you tell me what is the recurrence relation for this program? What is the recurrence relation for this program? What will the recurrence relation? If I just ask you that what will the recurrence relation for this particular program, then what you will say? See here, you can say that this particular function is a recursive function first of all, right? Because this is a fun, and fun is calling fun itself. I hope you know what is a recursive function. So this is a recursive function first of all. So that is why you will be writing the recurrence relation for the time complexity. Okay, so which means you are writing a recurrence relation, and where this tn is a time complexity, right? Time complexity if input is n, right? For input n, right? For input n. Now how you can write it? Since you are calling yourself, I mean this function is calling itself, so which means that like initially you are calling with n, now you are saying that okay, now you are calling with n by 2. So what will the time complexity relation? Can you tell me what will the time complexity relation that you need to write? Okay, so it will be t of n by 2 plus some constant, isn't it? It will be t of n by 2 plus some constant. Let me know if that is fine, right? So this will be t of n by 2 plus some constant, which means that the recurrence relation for this particular program will be t n by 2 plus some constant, right? Why that is constant? Because anyway all the statements like else, return, or any other statement, if these things and any other statement, so that will be taking at least constant time, so that's why you need to write the constant, right? So tn equal to t n by 2 plus constant. Now tell me what will the recurrence relation? See, currently I'm just asking you what is the recurrence relation, and then we will see that how to solve it, right? Then we will see how to solve it. Can you tell me what is the recurrence relation for this program? What will be the recurrence relation for this program? See here, it will be tn equal to, should I be writing? Okay, let me just ask you, should is it correct? Let's say it is option A. Option B is tn equal to t n minus 1 plus 1. Option C is tn equal to n t n minus 1 plus constant or plus 1, and option D is tn equal to t n minus 1 plus n square. So what is the correct answer here? Can anyone tell me what is the correct answer? See, what you are doing, you are calling tn minus 1, that is good, and then I mean you are calling with n minus 1 input, so that's why tn minus 1 will definitely be there. But how many times? Only one time, not n times, right? So that's why this c is anyway state of a reject, right? C is anyway state of a reject. Now you need to check that, see here you are adding n. It doesn't mean that you are adding n in the recurrence also. See, this addition will take just constant time. That's why B is the correct answer. See, when you will be having n in the recurrence, whenever you are doing n amount of work, are you doing n amount of work? No, right? See, if I just ask you that what will the recurrence relation, instead of this program, if I just ask you what will the recurrence relation, okay, let's suppose for this program, I mean here I have something like this. Okay, maybe I can write something like this. Let's suppose if I just ask you what is the recurrence relation for this program, an, and here if n is less than or equal to 1, then return 1 or whatever, right? Return 1. Else here, let's suppose I write a for loop for I equal to 1 to n. Okay, and let's suppose I write a for loop, and then I do some plus equal to I, and then then here I call, after that let's suppose I call a of n minus 1. Then what is the recurrence relation? See here what I'm doing, I am using this for loop. If I'm using the for loop, then I'm doing n amount of work, right? Then I'm doing n amount of work. Otherwise, I'm not doing n amount of work. See here, I'm just doing the constant work, right? But let's suppose I ask you that instead of doing the constant work, I'm doing n amount of work. Then what is the answer? Then in this case, okay, in this case, what is the answer? A is the answer. Okay, in this case, A is the answer. See, let me just give you more example. Let's suppose I just ask you this. Okay, let's suppose I ask you this. There is a function fun n, and let's suppose I say this is basically having some base case, and let's suppose I say that you do else you do return 2 of t n by 2. Okay, then sorry, fun n by 2, not t n by 2, 2 of fun n by 2. Then what is your recurrence relation? Can you tell me the recurrence relation? Let me just give you the options. Okay. See, first of all, you should know that how to write the recurrence relation, and then only you can work with that, right? So let me give you the options. So option A could be you can say that Tn equal to 2Tn by 2 plus 1 or plus C, some constant, right? And then Tn equal to Tn by 2 plus some constant, or maybe Tn equal to Tn by 2 plus n, or maybe the last option is that, let's suppose this is A, this is B, this is C, and maybe the last option, which is D, could be Tn equal to T n by 2 plus, let's suppose this is let's suppose n square. Then what will be your answer? See here, you just need to observe one thing, that I am calling this fn by 2, right? I am calling fn by 2 only once. I am calling this fun n by 2 only once. So you want to be multiplying 2 in the recurrence. Why you are multiplying 2 in the recurrence, right? So that's why B is the correct answer here, right? So here in this case, B is the correct answer, because you are calling only once. You are not calling it twice. So that's why A is not the correct answer. But let's suppose if I ask you this, let's suppose here if I just say that this is plus fun of n by 2. Let's suppose I call it twice, then what will the answer? If I call it twice, then what will the answer? Then in that case, A is the answer, right? Then A is the answer. See, if I'm calling it just once, this is just one time calling, right? If this is just one time calling, one time. Okay. If this is just one time calling, then B is the answer. If this is two times calling, then A is the answer. Okay. I hope you understood that when A is the answer and when B is the answer, right? So this should be clear to everyone. Let me know if there is any doubt here, that are you confused that when is A answer or when is B answer? Are you confused in this, or that is okay to everyone? Let me know. Okay. Now let's just go to the next thing. So this is what that how to write the recurrence relation. Now let's just see that how to solve the recurrence relation, which is a topic of today, right? Solving the recurrence relations. Okay, this is a topic of today. Now there are three popular methods. One is iteration method or repeated substitution. Okay, another one is recurrence tree method. Another one is Masters method. So let's just see each of them one by one. Let's just start with the iteration method or repeated substitution method. Okay, so let's just start with the iteration method, or we also call it repeated substitution method. Now let's see this question number 1. Can you solve this? Okay, here I'm assuming in all of the cases I'm assuming t1 equal to 1. Okay, the base case is 1. I'm assuming the t1 equal to 1. Okay, so Amrut is asking here in this particular question, Amrut is asking that we can rewrite this particular thing. Okay, we can rewrite this particular thing as this particular thing as f fun of n by 2 plus fun of n by 2. Then why not A is the correct answer, right? See, it's not about how we can write, right? It's not about how we can write. It's about what is written here. See, here it is written 2 into fun n by 2, which is very good, right? This is a foolish thing, right? This is just unnecessarily you are calling it twice. See, you can call it once and then you can multiply by 2, right? If you can do that, then it is better, isn't it? If you can do that, then it is better. If you're calling it twice, then A will be the answer, and it is not a good thing, right? It is not a good thing to call it the twice if you can do just in one thing, right? So it's not about what you can write. It's not about what you can write. It's about what is already written. Okay, what is already written. So you can say this is just like an optimized thing, right? This is just like optimized thing, right? Okay, what it is written. It's about what it is written. Okay. Now let's see this question number 1. And currently we are solving which method? We are solving using iteration method. So which means we will be repeatedly substituting. So here Tn equal to this, then what you can do? You can write Tn minus 1 as, can you tell me what will be the Tn minus 1? It will be Tn minus 2 plus 1, isn't it? See, here this is given to us, right? This is given. Okay, this is the question. This is given to us. Now we are writing the solution. Okay, so now the next thing is basically solution. So this is solution. Okay, so now we are solving. So here I am saying that if Tn is given like this, then Tn minus 1 can be written like this, which means that Tn, instead of Tn minus 1, I will be substituting it to Tn minus 2 plus 1, and then this plus 1 was already there, right? This plus 1 was already there. See, what I'm saying here is that this Tn minus 1 is basically substituted as this whole thing. Okay, this whole thing is Tn minus 1, and then this plus 1 was already there, and this Tn minus 1 is this. Is this okay to everyone? So if you understood this, then let's just do one thing. Then we can basically expand it further. See, we have got Tn equal to Tn minus 2 plus 1. That is because of Tn minus 1. That is because of Tn minus 1. Right? And then plus 1. And then plus 1. Okay. Now let's just do one thing. Let's just unroll this Tn minus 2 one more time. So what will the Tn minus 2? Can you tell me? See, if you put Tn minus 2 here, then it will be see here. See, Tn minus 2 will be just 1 lesser than this, then plus 1, isn't it? Just 1 lesser than this. So which means Tn minus 3 plus 1. So that's why you just put it here, right? You just put this Tn minus 2 here. So that's why what is the answer? This will be Tn equal to, you just put this Tn minus 2. So this will be Tn minus 3 plus 1. This is Tn minus 2. And plus 1 was already there, and then plus 1 was already there. So basically this is ultimately, if you want at this point in time, you can just add it. This is Tn minus 3 plus 3, right? This is Tn minus 3 plus 3. Now can you do it further, and can you keep on doing it? So if you keep on doing it, then there will be the case where you will be getting Tn equal to T of n minus k, right? So n minus, if I just ask you what is the value of n minus k plus k, then you will say that, see, if this is n minus k, then in the summation it will be plus k. See, if it is n minus 3, then we have observed that this is plus 3, right? Similarly, if it is n minus 2, then this is plus 2. So that's why if it is n minus k, then this is k. Now just see the base case. The base case is that T1 is what? The base case is that T1 is 1, right? This will be the base case that I am assuming. So which means n minus k, assume that to be 1, which means k will be n minus 1 or something, right? So basically, ultimately you can write Tn equal to, this will be T1 plus n minus 1, and then T1 is 1, right? So ultimately it is 1 plus n minus 1, which is nothing but what? Just let me know. So this value, can you tell me this value? This value will be just n, right? So finally n is your correct answer. So equal to, you can say this is equal to n. Okay, I hope you understood, right? I hope you understood that what is the correct answer. So let me know if you have understood this. So that's how you can keep on doing it, and then that's how you can solve this particular question, right? Okay, now let's just see this question. Can you solve this question? Let's just quickly solve this question. So this is Tn equal to, you are saying here, instead of 1, it is n, right? So you are saying that Tn equal to this. So what is the value of Tn minus 1? The Tn minus 1 will be T of n minus 2 plus n minus 1, right? So you can put now Tn equal to, T of n minus 1 will be T of n minus 2 plus n minus 1. This is just T of n minus 1 and then plus n, right? Now you have two choices here. Either you can add these two. Okay, if you want, you can add these two. Or you can just keep it as it is. You can just keep it as it is. See, if you add these two, then what is the answer? It will be basically 2n minus 1. But currently, let's not add it. I want to observe the pattern. So that's why I'm not adding it, okay? So don't add the series, okay? Don't add it now, okay? Don't add this as of now, okay? So now you will be getting Tn equal to this thing, right? Now Tn minus 2 is similarly, Tn minus 2 will be similarly n minus 3 plus n minus 2, right? T of n minus 3. So this thing, similarly, this thing will be T of n minus 3 plus n minus 2, and then this n minus 1 and n is already there, right? So basically this is n minus 1, n minus 2, n minus 1, and then if you keep on doing it, then what is the answer? Yes, some of the people have already got the answer. So if you keep on doing it, then you can definitely tell me the answer. The answer will be here, you can say this will be t of n minus k, and then see, if it is 3, then it is till 2, right? n minus 1 till 2. So similarly, it is till k or k minus 1, doesn't matter basically, right? Plus n. So if this n minus k is k, n minus k is 1, and if this n minus k is 1, then what is the answer? This will be 1, okay? This will be 1. So basically this series will boil down to n minus 2 till 1, right? And then this is a AP series. This is AP series. So if you remember this AP series, this is n square, right? This is n square. Okay. This is summation of first n numbers. I mean order of n square. This is n into n minus 1 by 2. But you don't need to worry about the exact thing. We are just approximating in the asymptotic analysis. See, this particular thing, which is 1 plus 2 plus 3 till n. If you remember, this is n into n minus 1 divided by 2, isn't it? Sorry, this is n into n plus 1 by 2, right? Because if n is 1, then this is going to be 1. Yeah. So it is n into n plus 1 by 2. Okay. So this series, right? This series that we have got is n into n plus 1 by 2, but you don't need to worry about the exact thing. You can just say theta of n square. Okay. Theta of n square, which is perfectly fine. You can definitely say theta of n square, which is perfectly fine. I hope that is fine to everyone. So finally, what is the answer that we have got for this particular recurrence, which is Tn equal to t of n minus 1 plus n? The answer here is theta of n square, right? Which means Tn equal to theta of n square is the correct answer here. Okay. Now let's just see this question number 3. What they are saying here, they are saying that that this is Tn by 2 plus n. Okay, Tn by 2 plus n. So let me just solve it. Now, what is the Tn by 2? It will be T of n by 2 square plus n by 2, isn't it? So finally, your T of n will become what? It will become T of n by 2 is T of n upon 2 square plus n by 2. And then plus n is already there, right? Plus n is already there. Now what is T of n by 2 square? What is T of n by 2 square? It is T of n by 2 power 2 square and square, right? 2 power 4. Sorry, this will be, see, you are finding T of n by 2, which is T of n by 2 square. And then if you find T of n by 2 square, then it will be a 2 of, like you need to divide by 2. So T n by 2 cube plus n by 2 square, right? See, whatever is the number here, you need to divide by 2, and then you need to write this number as it is here. So if you divide by 2, then it will be the case. So what is the answer here? This is T of n by 2 cube plus n by 2 square plus n by 2 plus n. Okay. So basically what we have got is just like this. See, what we have got is this. Let me just remove this and let me just write it here. So what we have got is this. Now tell me, if we have got this, then how to solve further? Do you need to add this or you need to observe the pattern? You need to observe the pattern, right? So just observe the pattern here. So what is the pattern? It is n by 2, n like this, right? So it is, now if it is T of n upon 2 power k, then you will say it is n upon 2 power k minus 1, n upon 2 power k minus 2, or whatever, right? You don't need to write these things, n upon 2 plus n. Now you observe one thing, that this I am assuming to be 1, right? So I am assuming here this to be 1, which means I am assuming that n upon 2 power k is 1, which means k is log n, right? K is log n. Now if this is 1, if this is going to be 1, then you can say 1 plus, the series will be 1 plus, or maybe I can write like this. This is n plus n by 2 plus n upon 2 cube plus ... till 1, right? Till 1. Okay. So now can you tell me what is the answer here? Yes. So basically this is a decreasing GP, right? Yes. So that's very good observation. So finally we have got T of n equal to n plus n by 2 plus n upon 2 cube till 1, right? So just see here, very, very carefully just see here. This is a GP, right? What is the ratio? What is the common ratio? The common ratio is 1 by 2, right? This is the common ratio. This is a common ratio. Now you just see here one thing. If this is a common ratio which is 1 by 2, then in that case, can you tell me that isn't it a GP? Yes, this is a GP. If this is a GP, then what is the common ratio? It is 1 by 2. Then is it a increasing GP or decreasing GP? It is a decreasing GP, right? It is a decreasing GP. If it is a decreasing GP, in that case, you will say the answer is approximately, like in asymptotic sense, answer is just the first term. Okay, the first term will always dominate. First term in GP. Okay. So see, if you want, you can definitely solve this. You can solve this a into 1 minus r power n upon 1 minus r using this formula. You can definitely solve it. And then you will realize that there is no point in solving this. Okay, there is no point in solving using this formula. If you want, I can solve this. See, if you want this n plus n by 2 plus n upon 2 cube till 1, right? So how many terms are there? I think approximately you can say this is basically log n terms, because n upon 2 power k, and which is just 1, right? So here the k terms are here and k just log n. So you can say these are the log n terms. Okay. So anyway, so basically the first term into 1 minus r power, r is 1 by 2, right? R is 1 by 2 power number of terms are log n upon 1 minus r. Right? So this is the exact summation. Now if you see this is just 1 by 2, which is constant. Now n minus this is 1 by 2. So this is basically, let me just solve this separately. This is basically 1 minus 1 by 2 power log n, right? Power log base 2n, which is nothing but 1 minus 1 by n, right? Which is nothing but 1 minus 1 by n, which is nothing but n minus 1 upon n, right? N minus 1 upon n. So this is into n minus 1 upon n. N will cancel out. This is n minus 1. So ultimately it is coming out to be theta of n only, isn't it? Ultimately it is coming out to be theta of n only. So that is why, right? So that is why, what is the correct answer here? Tell me. What is the correct answer? Just theta of n. So just theta of n is the correct answer. See, this is very good observation, that if you have decreasing GP, okay, if you have decreasing GP, then the first term is always the answer. Tell me, what is the answer here? Tell me, what is the answer here? Okay, in asymptotic sense, can you tell me what is the answer here? Let's suppose I write some formula like this. Okay, let's suppose I write n square plus, let's suppose I write n square upon 2 plus n square upon 2 square plus n square upon 2 cube. Okay, let's suppose I write some decreasing GP. Can you directly tell me what is the answer? Theta of what? Can you directly tell me what is the answer? This is going to be theta of n square. Why? Why that is the case? Because since it is a GP, okay, the first observation is that it is a GP, and that to a decreasing GP. So the first term is always the correct answer. Okay. So in the decreasing GP, just note it. In the decreasing GP, okay, first term is the answer. Okay. Now suppose there is an increasing GP, or maybe let me just ask you one more example for the decreasing GP itself. Let's suppose the GP is looking like this. Okay, this is n cube plus n cube upon 2 cube plus n cube upon 2 power 6 plus n cube upon 2 power 9, and so on, right? Let's suppose till 1. So what is the common ratio here? 1 upon 2 cube, right? 1 upon 2 cube is the common ratio. Isn't it decreasing GP? Yes, this is decreasing GP. So can you not tell me directly the answer? Yes. So what is the direct answer? Theta of n cube. Isn't it? So theta of n cube is the direct answer. See, it is a decreasing GP. If it is a decreasing GP, then first term is the answer, right? GP then first term is answer. Okay. Now tell me, suppose if it is an increasing GP, which means, let's suppose 1 plus, let's suppose it is something like this, 1 plus 2 plus 2 square plus 2 power 3 plus something like that, 2 power k. Okay, or maybe 2 power n, suppose 2 power n. Okay, then what is the answer? If it is an increasing GP, then what is the answer? If it is increasing GP, then see, if it is an increasing GP, okay, if it is an increasing GP, then the last term is the answer. Okay, the last term is the answer. Last term, okay, which is 2 power n. So Tn is going to be theta of 2 power n. Okay, if it is increasing GP, then last term is the answer. Now tell me what is the answer here? Suppose Tn is equal to 1 plus n square plus n cube, and then plus, let's suppose, n power 50. Then what is the answer? If it is increasing GP, then what is the answer? The last term, right? Theta of n power 50. This is increasing GP, then last term is the answer. Okay, last term in increasing GP. Okay. Now tell me this. Tn equal to n plus. Let's suppose this is Tn equal to n plus n minus 1 plus n minus 2 plus n minus 3 till 1. Then what is the answer? Is the first term answer here? Just let me know. Is the first term answer here? Just let me know. See, is this a GP first of all? Is this a GP? This is not a GP, right? See, this term, this particular thing is not the GP. This particular thing is not the GP. Is this okay to everyone? Since this is not the GP, that is why you don't apply the first term and last term, right? You are not going to apply the first term and last term. So since this is not the GP, so what you will say here? Just let me know what you will say. Here you can't determine using the first term and last term, right? Here you will say since it is AP, so that is why you will say this is theta of n square, right? It's not, you need to sum it up, okay? And AP, we know that this will be theta of n square. So this is not a GP, okay? This is not a GP, okay? I hope that is okay to everyone. Cool. Now coming back to this question, okay? So coming back to this question, here we observe that it is n plus n by 2 plus n by 2 square and so on. So basically, ultimately the answer will be theta of n only, because n plus n by 2 or this thing is just theta of n, right? Okay. Now let's just solve this question. Okay, let's just solve this question. Can you try solving this? This seems to be tricky question, right? So let's just try solving it. See here in this particular question, okay, in this particular question, what is happening? Let me just know. See, let me just tell you that what is happening. Here, this Tn is given like this, right? Now what you will say? You will say that if Tn is given like this, then what you will say? You will say that here this Tn is this, and then if we are using substitution method, then you need to basically repeatedly substitute. Then Tn by 2 will be what? Tn by 2 will be 2t n by 2 square plus n by 2 log of n by 2, isn't it? Right? Okay. So that's why this Tn will become 2 of t n by 2 square plus n by 2 log of n by 2 plus n log n, right? Plus n log n. So basically you will be writing this Tn by 2 here. Okay, this is Tn by 2. Okay. Now can you just rewrite it again? Can you just write t of n by 2 square? See here what I'm saying. Let me just tell you again. See what I'm saying, that this particular term, which is Tn, right? If you rewrite it, then you will say this Tn is going to be 2 of Tn by 2 plus n log n. Okay. And what is this 2 of Tn by 2? You need to write it carefully. It is nothing but this particular term, right? It is nothing but this particular term. So that's why you will be writing it 2 of Tn by 2 square plus n by 2 log n by 2, isn't it? Okay, so let me just rewrite it. It will be 2 square t of n by 2 square plus n log n by 2 plus n log n, isn't it? Okay, now let me just open this again. Okay, let me just open this again. Now can you tell me what will be t of n by 2 square? It will be 2 of, see, whatever is the number you need to divide by 2, right? 2 of t n by 2 cube plus this is n by 2 square, right? N by 2 square into log of n by 2 square, isn't it? Right? Let me know if that is okay to everyone. Okay, so how you will be solving it? You will be like I am currently solving using the repeated substitution. If you want, you can use the Masters method. Okay, don't worry about it. We can definitely use the Masters method, but currently I am using the recurrence. I'm repeated substitution. Okay, I'm solving this using the repeated substitution. Now, can you tell me how to rewrite it? Let me just remove it for the more space. Okay. So see here, currently we have got this. Currently, this is the Tn that we have got. This is the Tn that we have got, right? This is the Tn. Now, can you just substitute? Can you just substitute this thing? So 2 square into something into this thing, and then plus the rest things are as it is, which is n log of n by 2 plus n log n, right? And then what is the rest thing? This particular thing has to be substituted. So it is nothing but 2 into t of n by 2 cube plus n by 2 square into log of n upon 2 square, isn't it? Okay. Now can you just solve this further? Let's just see now I think I will be able to analyze the pattern. So what is the pattern that we are getting? It will be 2 cube into t of n upon 2 cube plus n into log of n upon 2 square plus n into log of n upon 2 plus n log n, isn't it? Now if it is 2 power k, okay, if it is 2 power k, then t of n upon 2 power k, and then plus then it will be, see, if it is 2q, then it is 2 square, right? You can take n common if you want. Then log of n upon 2 power k minus 1 plus log of n upon 2 power k minus 2 and so on, right? And then it will be log of n by 2 plus log n. Okay, cool. Now can you tell me how to solve this? How to solve this last recurrence relation, or the last relation? How to solve this last particular thing? Can you tell me? Okay, just let me know. See, this particular thing can be solved like this. This is Tn, right? Now I'm assuming that this is 1, which means k is log n, right? Or 2 power k is n. So 2 power k is n. This is my assumption. Or k is log n. Okay, so it will be 2 power k is n. So it is n into t1, right? So it is n into t1, which is 1, plus there is some term which is n into this thing. So if 2 power k is n, then this will be n by 2, right? This is n by 2. This term is n by 2. So log of n by 2 plus this will be n by 2 square, log of n by 2 square, and then, okay, see, this will be log of n by, no, sorry, this is not log of n by 2. Now here we are saying that n upon 2 power k minus 1, that is the value we want to know, right? So n is 2 power k, and we want to know n upon 2 power k minus 1. So you can divide by 2 power k minus 1 both sides. So this will be just 1 upon 2 power minus 1. This is just, I think, just 2, right? So this value will be 2. So log 2 plus log of 2 square, and then so on, right? Or maybe you can write in that way. You can write in that way that it is log of n, right? Okay, see here it is, you can write this term first. You can say this is log of n, and then plus log of n by 2 plus log of n by 2 square, and so on, and ultimately log of 1 or log of 2 or whatever, right? Ultimately it is 1. Okay, now can you tell me what is this summation? How to solve for this summation? Can you tell me what is the summation? Just let me know that how we can solve for log of n plus log of n by 2 plus log of n upon 2 square, and so on. How we can solve for this summation? Okay, just let me know that what you are getting. So what you are getting? See, this n is, what is this n? N is nothing but 2 power k. So if you want, you can solve like this also, right? So here, if you want, you can also multiply. So what it will be? It is n into, or maybe if you want, you can solve like this also. You can say this n is nothing but 2 power k, right? So this series is nothing but n of n is nothing but 2 power k. This is log 2 power k minus 1 and so on, right? So on. So this is basically k plus k minus 1 and so on, right? So ultimately it will be k square, order of k square, and k is what? Log n. So it will be order of log n square, right? It will be order of log n square. See, ultimately this is what? This is 2 power n is 2 power k. So if you want, you can simplify, instead of log, you can simplify it as a normal term. This could be k, this could be k minus 1, this could be k minus 2 and so on. So ultimately this is k square. So finally what you are getting is basically something like this. See, finally what you are getting is something like this. You can say this is n plus n into k square. K is nothing but log n, right? K is nothing but log n. See here, k is a log n. So hence this particular term is n plus n into log n square. So that's why this is insignificant term. So n log n square is the answer here. Okay, and log n square is the answer here. You don't need to multiply all of the log n. So someone in the chat is suggesting that we can multiply all of the length. So you can do it, but in the recurrence, so you will get to understand more with the examples, that in the recurrence we will prefer that if we can avoid the log and all, right? So we can avoid the log here. How we can say that, okay, this is this term log n is nothing but k, right? Log n is nothing but k. So that's why what we are getting is just k square. This is k minus 1. So ultimately this will be n log n square. Those who are familiar with the Master's theorem, can you also solve this as using the Master's theorem? Tell me. So those who are familiar, so we will see the Master's theorem in a couple of minutes, but those who are familiar, can you also solve using the Master's theorem? See, what is fn? N log n, right? So I'm just solving using the Master's theorem. Those who are familiar, otherwise in just 10 minutes you will get to know the Master's theorem more. Okay, so this is fn, and what is n power log base ba? So n power log base ba is, so this is n. So if it is n log n, and if it is n, then what is the answer using the Master's theorem? It is a multiple of log n. So using the Master's theorem, you can know that this is n log n square, right? N log n square. So using the Master's theorem also you can do it if you are familiar. But don't worry, we will get to understand the Master's theorem in a couple of minutes. But here I want to solve using the repeated substitution. So here you can observe this log n is just a k. So that's how you can solve this, right? Okay. Now can you solve this? This is easy question. Can you try solving it using the repeated substitution? Okay, so you can definitely try solving it, and then if you see, then n log n is the answer here. So what you can do, see here, this will be 2 into t of n by 2 square plus n by 2 plus n, isn't it? And then if you do it one more time, then I think this will be n plus n by 2 plus n by 2 square and so on, right? So ultimately 1. Okay, ultimately 1 most probably. Or should we solve this? See, the answer is on the next page. Okay, so here the pattern that we are getting is basically is n plus n. Okay, the pattern that we are getting, it is actually a little interesting. So let me just solve this. Okay, so I want to convey here one thing, so maybe I can just quickly solve this. See here, if you just try solving it, then what you will be getting, it will be tn equal to 2 of tn by 2. Tn by 2 is what? Let me just write it separately. Tn by 2, it will be 2 of t of n by 2 square plus n by 2, isn't it? So here it will be 2 of t n by 2 square plus n by 2. Now you observe here, this is 2 square into t of n by 2 square plus n, right? Now if you keep on doing it, then can anyone suggest me that what you will be getting if you keep on doing it? See here that you have just got this, right? You have just got this. Now if you keep on doing it, then what you will be getting? You will be getting 2 power k into t of n upon 2 power k plus n plus n plus n, right? How many times? If it is 2, then 2 times. If it is k, then maybe k times, right? These are the k times. Okay, let's assume that this 2 power k is n. So this will be again n into t1, okay, which is just 1, right, plus n, which is k plus 1 times. So can you tell me what is the answer here? This is n into k or n plus 1 into k. And what is k? K I have assumed to be log n, okay, or maybe you can say that I have assumed that n upon 2 power k to 1. So that's why this is n into k, which is n log n is the correct answer here. Okay, n log n is the correct answer here. Let me know if you have understood this or there is any problem in doing this particular question. Let me know. Okay, now let's just solve the next question. This is question number 6. This is little interesting. We will be solving these kind of questions using other methods also, but for now let's just use the repeated substitution. Can you try this question? See, here they are saying Tn is this. Now can you tell me how to use a repeated substitution here? How to use the repeated substitution? Okay, let's just see, right? So how to use a repeated substitution in this particular question we are going to see now. See, this is the question which is given, right? Now let's just do one thing. Let's just say this is Tn, which is like this, right? Now tell me what is the value of t of square root of n? What is the value of t of square root of n? It is going to be, can you tell me what is this value? It is going to be square root of n and then one more square root, which means if I just ask you what is the value of t of n by 2, n power 1 by 2, then it is instead of n, it is n power 1 by 2 plus into the same thing, which is t of n power 1 by 4 plus t of this thing, right? So this is nothing but the whole thing is t of n power 1 by 2. So that's why you will be writing it, right? So this is nothing but square root of n into something plus n, right? And what is that something? This is n power 1 by 4 plus, into t into n power 1 by 4 plus n power 1 by 2. Isn't it? Let me know if that is okay to everyone. Let me know. Okay, this is little tricky question, so let me know if that is okay. Okay, so that's fine, right? Now let's just go further. Now what you will do, you will say that, see, this is ns power 1 by 2. You need to multiply by ns power 1 by 2. So it is ns power 1 by 2 plus 1 by 4 into t of ns power 1 by 4, right? Plus n, something like this, right? Plus n. Now what is this? This is, I think you multiply by 2. This is 3 by 4, right? So this is ns power 3 by 4 into t power n by 4 plus n. Okay, let me know if that is fine to everyone. Let me know if that is fine. See, what we did, we are substituting for t of square root of n, which is nothing but this n is instead of n you will be writing n power 1 by 2, right? And then 1 by 2 is already in the power, so that's why this is the thing. And then instead of this n you will be writing n power 1 by 2, so that's why it is power 1 by 2, which is 1 by 4, and then power 1 by 2, right? Okay, now tell me what is the value of t of n power 1 by 4? What is the value of t of n power 1 by 4? See, t of n power 1 by 4 will be what? It is going to be, see, instead of n you are going to write 1 by 4, right? So it is going to be n power 1 by 8 into t of n power 1 by 8 plus n power 1 by 4, right? Okay, I hope that is fine to everyone. Now if you observe that you need to write, instead of this you need to write this whole thing, right? Instead of this you need to write this whole thing. Now that will get multiplied by n power 3 by 4, right? That will get multiplied by n power 3 by 4. So ultimately this will get multiplied by n power 3 by 4. This will also get multiplied by n power 3 by 4. So if you multiply this thing as n power 3 by 4, then this is nothing but n. So basically you will say, see, you will say here that, let me just delete all of this, right? So you will say here, this particular term that you have got is going to be this is equal to n power 3 by 4 and then this whole thing, right? Plus n plus n, right? What is this whole thing? This is n is power 1 by 8 into t of n is power 1 by 8 plus n is power 1 by 4. Now this is going to be, you just multiply this 3 by 4 here, which is going to be this 7 by 8, n is power 7 by 8 into t of 1 by 8, right? Plus n plus n plus n, right? Okay, I hope you understood. So what is the pattern that we are getting? See, let me write the pattern. See, initially we have got one thing, which is Tn equal to, what is the first thing that we have got is this one, right? T of n is equal to this thing, right? This is the first thing that we have got. So let me write it there. This is the first thing. And then if we did it further, then what we have got? We have got something like this. Okay, we have got something like this. So actually this is just for the practice, but maybe we will avoid all of this using some other methods. Okay, using some other methods, maybe we can avoid all of this. Now can you observe the pattern? So if you observe, then you will say that, see, summation of these two is anyway 1, right? And this is basically, if you unroll it one time, you will be getting n plus n. If you unroll it one more time, see, initially this is just n, but if you unroll it one time, you will be getting n plus n, and then if you unroll it one more time, n plus n plus n, and so on, right? Okay, so let's suppose that here whatever we are getting, okay, basically it is 2 square n upon 2 power, so n upon 2 square n upon n power 2 cube. So in this pattern we are getting the powers. So whatever we are getting, we ultimately want to say that this is going to be ultimately t of if it is 2 cube, then these are the 3 k's, right? If this is 2 power k, there will be something here, right? We can write that something, and then plus this is k times n, right? Is this okay to everyone? This is k times n, right? And what is this thing? This will be something which will give you 1 if you add these two, right? Okay, anyway, so I want this power to be, I want this thing to be 2. Okay, so I want, maybe this went little lengthier than I was expecting. Okay, anyway, so I want this n is power 1 upon 2 power k to be 2. So from here you can say 1 upon 2 power k is if you take the log, then it will be like this, that 1 upon 2 power k into log n is 1. So 2 power k is again log n. So k is log n. Okay, so k is log n. So that's why this is n into k, which is n into log n. Okay, n into log n will be the answer. Is this okay to everyone? N into log n. Okay, so yeah, this is little tricky, little interesting also. So what we have done here, you just see here what we have done. We have started with this, then we have just unroll it, right? Just unroll it. Just see the pattern. See, currently you might not be able to observe the pattern, but if you unroll it one more time, then we have got this. Now we have written both of the unroll, like this is one time, then one more time. Then we have observed that, okay, this is 2 square, this is 2 power q, right? And then summation of these two powers is anyway 1. So that's why this is ultimately going to be 1 upon 2 power something, right? N power 1 upon 2 power something. So I wrote it 1 upon 2 power k. Now the base case is given to us that t of 2. The base case is given to us as t of 2. Okay, t of 2 is 1. So that's why, because of this base case which is given to us like this, I assume that this is 2. And then finally we have got k value is log n. Okay, currently we can't use the Master's theorem, but we will see one very nice thing which is called change of variable method. Okay, so we can definitely solve it using the change of variable method. Okay, there is a different method which is very interesting also. We can't use Master's theorem here. I will tell you why, but we can definitely use change of variable method, which is very interesting and very easy. So using that method you can solve this. Okay, I will show you change of variable method. Okay, I will show you, don't worry. But if you want, you can use a substitution method. This will be little lengthier, but change of variable will be very easy. Okay, so which line you want me to explain from here to here? Sonamata is asking that please explain the last line. Okay, from where to where? From here to here are you asking? Okay, so see here that I am saying that it will be n, like whatever is happening, n is power 2 power q. Okay, 1 upon 2 power q. It is n power 1 upon 2 square. So that's why it will be n power 1 upon 2 power k, right? And ultimately I want that to be base case. So that's how I found out the value of k. Okay, that's how we found out the value of k. Understood? Okay, and then how to find this term? This term is nothing but summation of these two terms should be 1, right? Summation of these two terms should be 1. So if this is 1, this is 1 upon 2 power k, this will be 1 minus 1 upon 2 power k, because the summation of these two terms I want to be 1. Summation of these two terms, right? Okay, summation of these two terms, see, summation of these two terms, I want them to be 1. Okay, cool. But don't worry about this method. We will see change of variable method. That will be very easy to solve this question. Okay, what we will do in the change of variable method, we will divide by n. Okay, so we will say this is going to be, if you divide by n, this is going to be something like this. Now we can assume this particular term to be some other function. Okay, let's just assume this to be gn. If this is gn, if gn is this, then what is this? This will be g of square root of n plus 1, right? This will be g of square root of n plus 1. Okay, now we will assume n to be, okay, see what I'm saying here, that we will do the change of variable method in couple of minutes, but for now if I just reveal the suspense, then I will say that we will divide by n first. Okay, the first you divide by n, then we are getting this. Okay, we are getting this if you divide by n. Now after that I will show you the change of variable, don't worry. But if you divide by n, you will be getting this. But if you like, I'm just telling you in the advance, but we will go step by step, because these are the few methods which we will be discussing. Now let's just assume that to be g or s. Okay, whatever you want. Okay, let's just assume this to be g or s, and then we will assume n to be some 2 power m. Okay, we will assume n to be some 2 power m. Then this is something like this, right? G of 2 power m by 2 plus 1. Or maybe first you can do one thing. First maybe you can assume n and then you can put at g. Okay, doesn't matter. So now can you solve this? Can you solve this particular recurrence? Tell me. See, this is very easy. You are saying whatever you are having, just divide by 2. So how many terms it will be? If this is let's suppose x, and then x by 2, right? You are dividing by 2. Then log x, it will be the complexity will be log x, right? Complexity will be log x. So that is why here the complexity will be log of this, right? Log of this. So which means it will be m. So this will be just theta of m. Okay, this will be just theta of m, and then m is just log n. So that's why you can say this is theta of log n. Okay, and then okay, maybe I can just show you step by step, see what is happening. Till now I hope that is fine, right? Till now I hope that is fine. Now let's just see how to solve this. Okay, so this particular term, which is this one, this particular term is going to be g of 2 power m. If you want, you can assume that to be some sm or something. Okay, but let's not do it, because I have already done it and you will get confused if I do it 2 times in just one question. So it will be 2 of m by 2 plus 1, and then can you substitute this 2 of m by 2 with something? Can you tell me what is this 2 of m by 2? It will be g of 2 power m by 2. It is nothing but g of 2 power m by 2 square plus 1, right? 2 square plus 1. Okay, then that is why it is g of 2 power m upon 2 square plus 1, right? Okay, now I'm just asking you that how many such plus ones will be there? Okay, or maybe if that is again confusing you, so what you can do, let me just use one function. Let me not use 2 functions again and again. So maybe I can just show you from here. See, let me just explain you step by step. Is this okay till now, everyone? Let me know. Right, I have just divided by n. Okay, so I want to solve this question. I have just divided by n. Now what you can do, you can assume, let's just have a step 1. Okay, assume n to be 2 power m. Okay. See, we will see the step by step this method later on, but currently I am just telling you. Okay. This is 2 power m upon 2 power m equal to t of 2 power m by 2. Okay. Now, if this is s of m or g of m or whatever, if this is s of m, then what is this? S of m by 2. Right? So basically, finally you can say that this is going to be s of m equal to s of m by 2 plus 1. And this is just like a binary search, right? Can you tell me what is the prime complexity here? This is log n, right? Log m. You can definitely solve it. This will be log m. Now we know that finally we have got s of m is log m. Okay. See here that we have got s of m as log m. But we need to get the answer of t of n. So see here that s of m was nothing but t of 2 power m upon 2 power m, right? So this was nothing but t of 2 power m upon 2 power m is basically log m, right? So from here you can say that t of 2 power m we got 2 power m into log m, but we want t of n. So what is the relation between n and 2m? This is the relation, right? So this is nothing but n equal to 2 power m, right? So in other words, m equal to log n. Okay. In other words, m equal to log n. So basically this is t of 2 power m is what? N, right? 2 power n m is n equal to 2 power n is m, and log of m is what? M is log n, log of log n, right? N into log of log n. Okay. See, n into log of log n is the only answer that we have got earlier, and also here also we have got the same answer. So don't worry, we will do it step by step. Okay, don't worry, we will do it step by step. In just couple of minutes I will show you this change of variable as a method. Okay, so don't worry about it. Now let's just see the tree method. So currently we have seen the substitution method. Okay, let's not worry about this question if this is very tricky for you. Okay, but apart from this question, I hope every other question is fine. Okay, and this question also we have solved. This question also we have solved using two methods: substitution method and also change of variable. I will show you change of variable later on. Okay, currently if you have not understood, don't worry, it is a very powerful, very nice method. I will show you. See, using this method you can solve many complex questions very easily. So I will show you this method in couple of minutes. But for now, let's just see tree method. So what does this tree method says? Okay, let's just see this question directly. This says that there is a recurrence relation. Let's suppose this is a recurrence relation, and if you have written like this, then you can solve this using a tree. How? Let me just show you. See, this recurrence relation which is written here, let me just solve this recurrence relation using a tree. So how? See, this is Tn which has been divided, this work has been divided into n by 5 and 4n by 5. And this is the cost of division. Okay, this is the cost of division. That's what we call. This is the cost of division. Cost of division. Okay, so we call it cost of division. Basically, whatever is the cost of division. Okay, I'm not. Let's suppose this is n square. So I'm not writing the cost of division here, which means I will say that n has been divided into n by 5 and 4n by 5. Okay, which means even this is n square. I'm not writing n square here. This is not the n which is here. Okay, so let's suppose this is the n. Okay, this is not the n which is here, this is the n which is here. Basically I'm dividing the n into two parts. Okay, that's how we are solving. Now further you are dividing that n into two parts. So how to get those two parts? You can say that if you want to get the left part, you multiply by 1 by 5. If you want to get the right part, you multiply by 4 by 5. So if you multiply by 1 by 5, you will be getting this. If you multiply by 4 by 5, you will be getting this. If you multiply by 1 by 5, you will be getting this. If you multiply by 4 by 5, then you will be getting this. Is this okay to everyone? Let me know. See, what I'm doing, I'm saying that this particular n has been divided into two parts, right? And further I'm dividing each of them into two parts. So that's why I'm getting this. Now what we will do, we will say again, okay, we will say again that, see, now we can divide further, right? Now we will say again that we can divide this also further. this also further, right? Now tell me, if you keep on dividing these, okay, then there is a leftmost branch, there is a rightmost branch. There are two branches, right? I mean, there are many branches, but let's just focus on this just two branches. Now here you will be writing something like this, right? You will be writing something like this, okay? And here if you notice, then you will be writing, I mean, there will be the rightmost branch, then you will be writing something like this, 4 upon, I mean, this branch may be little longer, okay, 4 upon 5 power k n. See what is happening here, you're dividing this n, and then you're dividing these two, and so on, right? So now what I'm saying that when you keep on dividing, tell me how to divide this. This will be 1 by 5, 1 by 5, and so on, right? Now you are dividing by 5 here, you are dividing by 5 here. In the rightmost, what you are dividing, you can rewrite it in other words, 5 by 4 you are dividing, right? N upon 5 by 4 square you are dividing, and similarly ultimately n upon 5 by 4 power k you are dividing, right? So basically you are dividing like this, I mean, you are dividing by 5 by 4 here. So suppose there is a number n, or any number, you divide by 5, n by 5, n by 5 square, n by 5, okay, and there is a number that you divide by, let's suppose little lesser, let's suppose here it is 2, then n by 2 square, n by 2 cube, or any other number which is lesser than 5, maybe 5 by 4, okay, maybe 5 by 4, okay, let's suppose this number could be anything which is lesser than 5, maybe 5 by 4. If you keep on dividing by lesser number, then which branch will be higher, which branch will go longer? See, this branch will get early terminate, right? This branch will get early terminate, and this branch rightmost branch will get like at last terminate. So what I'm saying, see, the recurrence relation is given like this: Tn equal to and Tn by 5 plus T of 4n by 5 plus n. Okay, this is what you are getting. Now this n, okay, this n you are dividing into two parts. One is n by 5, another one is n by 4n by 5 or n by 5 by 4, right? Okay. Now you are dividing this also into two parts. Now there will be the case that, what I'm saying here, there will be the case that this branch, this leftmost branch will be something like this, which will get early terminated, and there are many other branches here and there, right? There are many other branches here and there, but the leftmost branch will get early terminated, and the rightmost branch, which is, okay, this is 5 by 4, right? Okay, this is 5 by 4 power k. This will get later terminated, which means it will get early terminated, which means what? That there in between there are many branches, something will get terminated, something not, but this is the very first branch will get terminated, which means this is the time that we will be hitting the base case very first time. This is the time we will be hitting the base case later on. Okay, so anyway, so there are two branches, I mean, there are many branches, but the leftmost will get most early terminated, and the rightmost will get late, I mean, at the last it will get terminated. So here, how many steps you have taken to terminate it? K steps, right? K steps, or maybe you can say K1, and similarly here this will be K2. Okay, I mean, it will be basically later on terminated. Okay, see, at this node how much work you are doing? This is the work of division. Okay, so how much work you are doing? At this node you are doing n square, because this is the n. If this is the work of division, sorry, n, you are doing n work, because this is n. You are doing n by 5 work here. Okay, n by or 4n by 5 work here, which means ultimately at this level you are doing n work. At this level also if you sum this up, you will be doing n work. You are doing n work, right? At every level you are doing n work only. Okay, see, n work here. Why? Because this is n, so that's why n work here. Don't worry, you will get to understand more later on. If you want to divide this n by 5, then n by 5 work only. If you want to divide this 4n by 5, then 4n by 5. So basically n work at each level. Okay, n work at each level. So if these are the k levels, so how many levels it is? If each time you divide by 5, then these will be log base 5 n. See, if each time you divide by 5 upon cube and then so on, right? If each time you divide by any number, maybe 5, maybe 10, or any number, then how many times you can divide before you hit to be 1? Let's suppose last term is 1. Then you will say that, okay, n upon 5 power k is 1, then here 5 power k is n, then k is log n. K is log n. You might know it, right? Log base 5n basically. So if you are saying that you keep on dividing by 5, if you keep on dividing by 5, then ultimately it will be n upon 5 power k, which is 1, right? Which is 1. So that's why you can say that k is log base 5n, right? Log base 5n. So hence you can say that if you divide by 5, then ultimately the number of labels here will be log base 5n if you divide by 5. Now similarly, if you divide by 10, can you tell me after how many times you will be hitting 1, which means 10 is power k 1? How many steps will be there? If you divide by, keep on dividing by 10, then it will be log base 10, okay, base 10. And if you divide this n by a, n upon a cube, then after how much time you will be hitting 1? After how much time you will be hitting 1, or after how many steps you will be hitting 1, which means n upon a power k is 1. What is the value of k? Then you will say, if you are dividing by a every time, then base a, okay, base a, okay. So that's why if you are dividing here, if you are dividing by 5 every time, then this will be log base 5n. Okay, so till now log base 5n levels are there. At every level you are doing n work. Okay, so what I'm saying, let me just ultimately summarize this. See, t of n is t of n by 5 plus 4t of n by 5, t of 4n by 5 plus n. So basically you are dividing this n into two parts, n by 5, 4n by 5, right? Then n by 5 squared, then n by 5 cube, and so on, right? Okay, so basically at some point in time you will say it will get terminated, right? At some point in time there will be 1, this will be 1. Here you are dividing, but this is basically the last longer branch, and what I'm saying, this branch will get terminated first, right? There will be many other branches here and there, but this branch will get terminated last. So at every level you are doing n work. So n work because of this, n by 5 work because of this, 4n by 5 work because of this. So ultimately at this level also n work. So at every level you are doing n work. There are k levels here, which means log base 5 n levels. So how much work you are doing till this point? You are doing n log n, right? N log base 5n. So basically you can say your time complexity will be, your time complexity will be given like this. You can say that, see here, that you are doing, your time complexity will be, you can say it will be at least this, right? At least this. So basically you will say, the lower bound, right? The greater than equal to, or maybe you can say at least, or the lower bound, or maybe let me just say tn greater than equal to how much? This will determine by this, right? Log base 5n, and at every level work, right? These are the number of levels into work at every level. This is what? N. So basically you will say that it is nothing but n into log base 5n, which means tn is greater than equal to this. Okay, so using this branch you got to know that tn is greater than equal to this, right? tn is greater than equal to log n log base 5n, right? Similarly you will say that this will get end up with how many levels are there? Log, you are dividing by 5 by 4, right? So number of levels here is log base 5 by 4n. Okay, these are the number of levels, log base 5 by 4n, because you are dividing by 5 by 4 every time. So number of levels are this. So that's why tn is lesser than equal to number of levels and work at every level, right? And log base 5 by 4n. So tn is greater than equal to this, and tn is lesser than equal to this. Now this base won't matter, right? This base won't matter, as we have seen, right? This base won't matter. We have seen in the previous video also that this base won't matter. Which means if you want that, you can write it tn equal to tn. We are saying that tn is greater than equal to log base 5 n, and tn is lesser than equal to log base 5 by 4n. Now you can definitely convert this base to log base 5, right? Any of the base to any other base. How? You can say that log base 5 by 4 n is nothing but log base 5 log base 5, right? And now if this is n, you put it here, this is 5 by 4, you put it here. So this is n 5 by 4, right? So which means log base 5 by 4 n is nothing but log base 5 n upon log base 5 5 by 4, right? So basically this term is nothing but log base 5n because this is constant. So that's why these two terms are actually equal. So that's why you can just say that Tn is nothing but theta, right? You can write the theta here, which is theta of n log n, because base doesn't matter. Okay, so that's how you can solve using the tree method. Okay, see, you can solve this using the tree method. How? You will say that, okay, let me divide. Maybe you can solve this particular question, and then you can see if you are able to answer this particular question, right? So what to do here? You will say this n will get divided into n by 3, 2n by 3, right? N by 3 square and so on, right? And 2n by 3, 2 by n into 2 by 3 square, right? So basically you will be dividing by 3 by 2, or maybe you are multiplying by 2 by 3. You can say something like this. So which branch will get terminated first? This is, you are dividing by 3 here, you are dividing by 3 by 2 here. So obviously this will get terminated first, and then this will get terminated last. So this is n divided by 3 by 2, right? 3 by 2 power k. This is n divided by 3 power k. Now how many labels are here? You are dividing by 3, so that's why log base 3n. How many labels are here? Log base 3 by 2n, right? So you can say that at every level the work is n only, because this is n, right? This is the work, okay? This is n by 3 plus 2n by 3. This is n by 3 as work here. This is 2n by 3 is work, right? That's why the total work is n. So basically the number of levels, so you can say Tn is nothing but number of levels is log base 3n, which is greater than equal to, and it will be lesser than equal to. So that's why you can directly write theta of n log n. Okay, theta of n log n. Cool. Now let's just go to the next question. Can you solve this question? Here it is n square. It is going to be little interesting. Can you quickly solve this question? Let's just see if you can solve this question. Okay, it is going to be little interesting. The reason is that it is going to be n square here. See, here what we are going to do, we are again going to say we are dividing n. See, you don't write n square. I mean, if you want you can write it, but it will be not good for the understanding purpose. We are writing n only. Okay, the convention that I am following, this is n only. Okay, 2n by 3. Now again the same thing, right? The tree will be same. This is 3n square, and then this is also going to be 2 by 3 square n, and then ultimately it will get stopped at this. It will get stopped little later, and at what point in time? Can you tell me? It will get stopped at sometime later, right? Okay, so that sometime later will be n upon 3 upon 2 power k. So it is getting stopped here. In between there are many other branches. Okay, no worries. Now how many labels that we know? Log base 3n. How many labels that we know? Log base 3 by 2n. Okay. Now you tell me that what is the work here? The work here is n square, right? This is the work, which means for n, I am doing the n square work. Now can you tell me the work here? This is n by 3 square. This is the work here is 2 by 3 square n square, right? I mean the square of this basically. So this is n square. Can you sum these two? This is n square upon 9 plus 4 upon 9 n square. This is I think 5 upon 9 n square, isn't it? This is 9. Yeah, this is 5 upon 9 n square. Currently we don't know what is the pattern. I mean, this is n square, this is 5 upon 9 n square. So what you can do, you can see one more time. Okay, you can see one more time. See here, let's just see one more time. See, this is going to be, this branch is going to be, you multiply by 1 by 3, you multiply by 2 by 3 here, right? So it is 2 by 3 square, and this is, you multiply by 1 by 3 on the left. So which means this is, so you multiply by 2 by 3, so 2 by 3 square, yeah. So if you multiply by 1 by 3 here, it will be again 2 by 3 square, right? Okay. And this, right? So if you take the square again, and then you add all of this, okay, see here, this will be n square by 9. This will be n square by 9 square basically, right? This is going to be 4 n square by 9 square. This is going to be again 4 n square by 9 square. This is again going to be 4 upon 9, right? So 16 upon 9 n square. So can you add all of this? This is n square by 9 plus 4 n square by 9. So n square by 9 square, 4 n square by 9 square plus 4 n square by 9 square plus 16 n square. Okay, this is 16 n square by, this is n, 16 n square by 9 square, right? Okay, so if you add this, I think this is going to be 25 n square by 9 square, right? Okay, so which is nothing but 5 upon 9 whole square n square. So which means at this level I am doing the work 5 upon 9 whole square n square, right? So basically at every level I am doing, at this level I am doing n square, at this level I am doing this, at this level I am doing this. So how many levels are there? Okay, see, at every level, so what is happening? This was the question, right? Here I am dividing this into two parts, right? So what are those parts? Let me just write the question once again. Okay, see here that this is the question that is given to us, right? Now what we are saying, we are dividing that into two parts. One is n by 3, another one is 2n by 3. Now we are dividing again into two parts. One is n by 3 square. This one will be, you multiply with 2 by 3, so 2n by 3 square. Again this one will be 2n by 3 square. This will be 2 by 3 square n, right? Okay, and then you keep on doing it. We noticed that this branch will get early terminated, this branch will get later terminated. This branch is n upon 3 by 2 power k, this branch is n upon 3 power k. Okay, now let's just see that how much work we are doing. Here we are doing n square because this is n square. So here how much we are doing? Here we are doing n square upon 9. Here we are doing 4n square upon 9, right? So ultimately we are doing 5n square upon 9. Okay, now here we are doing n square, okay, n square upon basically n upon 9 whole square. So n square upon, you can say 9 square, right? This is 9 and n square upon 9 square we are doing. Okay, here we are doing 4 n square upon 9 square. Again here we are doing 4 n square upon 9 square. Here we are doing, this is already square, which is 4 upon 9. So we are doing 16 upon 9 square n square, right? If you sum all of this, this is going to be 25 upon 9 square, or maybe 5 upon 9 square n square. So you are doing n square, then 5 upon 9 n square, then like this, right? Now if there are k levels, let's just solve for the leftmost part. If there are k levels, then what you will do? If there are k levels, then you will say that this is, okay, let me just solve for this particular part. Then you are first doing n square, then you are doing, then see, let me just go to the next page. You are doing n square, then you are doing 5 upon 9 n square, then you are doing 5 upon 9 square n square, right? Then you are doing something, okay, 5 upon 9, I mean ultimately at the last you are doing this much. Is this okay to everyone? Now it will depend the value of k. The value of k for the lower branch, leftmost branch, can you tell me what is the value of k? It will depend, right? It is log, for the leftmost branch, log base 3n. For the rightmost branch, it is log base 3 by 2n or something like this, right? But actually you don't need to know the value of k. Why? First of all, tell me, is this decreasing GP or increasing GP? Okay, Tn will be something like this. Tell me, this is decreasing GP or increasing GP? This is definitely decreasing GP, right? This is decreasing GP. So that's why just n square. Okay, just n square. Okay, you don't need to even worry about the value of k, just n square. Why? Because this is the decreasing GP. Let me know if that is understood or there is any issue here. Okay. Okay. So let me know. Let me know if you have understood this. Right? Because this is a decreasing GP. Decreasing GP. Okay. Understood, right? Cool. So basically you don't need to even calculate what is the value of k for the leftmost, for the rightmost, and so on, right? So you don't need to calculate. Understood. Now, interestingly, we don't need to do all of this also. Okay, we do not even solve using tree method. Can you tell me any method using which we can solve this particular question? Let's suppose this is the question. Can you tell me any method? Can you tell me any method using which we can solve this particular question? Tell me. See, see, if those who know the substitution method, like substitution method, we have already seen, it will be very complex to use the substitution method if we are using 2t. Okay, if we are using t of something and then t of something, if there are 2t, if the form is like this, okay, t n minus 1 plus 1, then substitution is good. Okay, there is only one t, then substitution is good. If the two t's, then substitution will be very complex. So we want to basically solve this question, and I'm saying that we don't need to use the tree method. Okay, we don't need. Okay, I'm saying we don't need Master's theorem. Obviously, we can't apply. Then how? What we can do? We can say this is the thing, right? We can say that this particular relation. Okay, if you want, let's suppose if you want the lower bound. Okay, lower bound, and let's suppose here you want upper bound. If you want the lower bound, you can say that Tn is nothing but this is Tn by 3. Okay. See here, which one is greater? I think this is greater, right? This is greater. So let's suppose, because this is 2 into something, right? This is 2 into n by 3. So let's suppose I write this also as n by 3. Okay. I'm saying I'm doing the lesser work. Okay. I'm doing the lesser work. Which means 2t n by 3 plus n square. Isn't it? So you can solve this. Okay, you can solve this. Tn equal to this, right? You can solve this. And then you can solve this here also. You can solve this. So you will be getting lower bound and upper bound like this. Here you write both of the terms at edge. This term also as 2n by 3. So basically you write both of the terms and then you solve this. You will observe that this is also going to be theta of n square and this is also going to be theta of n square. Okay, that's why if the lower bound and upper bound both are theta of n square, then this is also theta of n square. Which means if you solve this relation, okay, what I'm saying, if you solve this relation, and then I'm just saying that you treat it, okay, once you treat it like this, and once you treat it like this, you can see this is nothing but the leftmost branch, isn't it? This is nothing but the leftmost branch. Okay, this is almost same as the leftmost branch. And if you do something like this, then this will be 2t 2n by 3 plus n square. This is also almost same as the rightmost branch. Then you solve both of them, right? If you know the Master's method, you can definitely solve. So you solve both of them, then you will be getting n square here, right? If tn is you can say greater than or equal to n square. If tn is lesser than or equal to n square, then tn is actually theta of n square only. Okay. So instead of using even the tree method, maybe you can do something like this, right? You can do something like this. Understood? Okay. Let me know if that is okay to everyone. Okay. Now let's just solve this particular question using the tree method. So can you solve this? Let's just quickly try. Okay, let's just quickly try to solve using the tree method, and then we will go to the other methods which are more interesting than tree method. Okay, so let's just see. So see here, here you are having n. You are dividing into n minus 1, n minus 2, and then this will be n minus 2, n minus 3, and so on. and this is n minus 3, n minus 4. Now tell me, what is the branch that will get that will first get terminated? This branch, right? This is n minus k, and it will first get terminated, and this will last get terminated, because you are just substituting, you are just subtracting by 1, and here you are subtracting by 2. So sorry, you are subtracting by 2 here, so this will first get terminated. This will first get terminated because you are subtracting by 2. So that's why this will first get terminated, which means this is n minus k. This will be very last get terminated, right? Okay. So Anam is asking that why we should be writing it like this. See, I'm just saying for approximation, I mean, you can say that, okay, this is summation of these two terms, right? This is the summation of these two terms. Now I'm saying that this is a lower term, right? Obviously this is a double work. This is a heavy recurrence, right? This is t of 2 of n by 3, right? This is just n by 3. It's like it is 2k. This is n. This is just k. So basically this is the heavy term. So I'm saying you replace the heavy term with the light term, which means you lower approximate, which is, it is basically lesser than, sorry, this is greater than equal to. Why? Because you are writing the lower term. So you are writing the lighter term here, right? So you are under approximating. Here you are over approximating. You solve for under approximation, you solve for over approximation, right? If you solve for under approximation, you are getting n square, which means you are saying that, okay, lower bound is n square, upper bound is n square, then it must be n square, right? It must be n square. So you can avoid using the tree method. That's what I'm saying. See, this is a heavier term, isn't it? Now I'm replacing with the lighter term, or you are replacing this lighter term with the heavier term. So basically you will be getting the lower bound and upper bounds. Okay, you will be getting the lower bound and upper bounds. So that's why you can say that you can solve using this method. If this is greater than equal to n square, less than equal to n square, then you are 100% sure that this particular recurrence is basically in between the n square. I mean, in between greater than equal to n square, less than equal to n square. This particular recurrence must be just n square. Okay. Cool. So this will get terminated first. Now, can anyone tell me, because I'm dividing by, I'm subtracting by 2. Can anyone tell me how many levels are there? How many levels are there? See, if you divide anything by a, then how many levels we get? N upon a power k. How many levels we get here? Can anyone tell me? We get log base a levels, right? Log base a levels. Okay. And if you, let's suppose, if I just ask you, if you subtract, okay, if you subtract, let's suppose, by b, can anyone tell me how many levels we get? If you subtract by any term, then ultimately this n minus kb is let's suppose 0 or 1 or doesn't matter. So basically we want this k, right? K will be nothing but n by b. Okay, n by b. So if you subtract, okay, or if you subtract, then you will be getting n by b levels, which means let me just tell you, if you subtract, let's suppose, by 1, tell me how many levels will be there. After how much time it will be 1? How many levels will be there? If you're subtracting by 1, so most probably you can just use the intuition that it will be after n times, okay, after n levels. If you subtract, let's suppose, something, okay, if you subtract let's suppose this n by 2, then after how many levels? N minus 6. After how many levels it becomes 1 or 0 or whatever, it will become constant after how many levels? N by 2, okay, n by 2, because you're subtracting by 2. It is very interesting, right? It is very interesting. N by 2. And similarly, let's suppose you have n, and if you subtract by 3, n by 6, n minus 6, n minus 9, and so on, then after how much levels it will become 0 or 1? N by 3, right? If you're subtracting by 3, then n by 3. So similarly, if you're subtracting by 1, then how many levels? N levels here, and here how many levels? N by 2 levels. So you can say these are the n by 2 levels, these are n levels. Okay. So at every level, how much work you are doing? Here, this work 1, here this is 1, right? So here you are doing 1, here you are doing 2, and then 1, 1, 1, 1. Here you are doing 2 square, which is 4, right? You are doing 2 square. At every level you are doing 1, 2, and so on, right? So you can say to solve this question, you can easily say that we can do something like this, right? we can do something like this, where we can say that okay, here if you want to solve this question, then you can say that this is going to be Tn is going to be 1 work, then 2 work, then 2 power 2 work, and then ultimately 2 power k work, where k will depend. Here this k is n by 2, here this k is n. Okay, anyway, but finally since this is increasing GP, can anyone quickly tell me what is the answer? Do you need to really solve it? No, right? This is theta of 2 power k, right? So, or maybe just 2 power k. So it is increasing GP. Now for this particular thing, for the left thing, and then for the right thing, what are the answers? 2 power k. What is the value of k for left and right? What is the value of k for left and right? See, for the left, the value of k is n. So Tn is basically 2 power n. Here Tn is 2 power n by 2, which means you will say it is not equal. Actually, you will say that here you are terminating first, right? Less than equal to, sorry, greater than equal to, and it is lesser than equal to, right? You are over approximating. Now this is interesting. This is going to be interesting. See here, this Tn is lesser than equal to 2 power n and greater than equal to 2 power n by 2. Are these two terms same? 2 power n, 2 power n by 2. Are these same asymptotically? No, right? So you can divide by 2 power n by 2 here, and this will be 2 power n by 2. This will be just 1. So obviously this term is 2 power n by 2 times greater. 2 power n by 2 times greater than this term. These two terms are not same, definitely. Since these two terms are not same, that is why you can't write theta. So theta is not possible here. Why? Because you are saying Tn is lesser than equal to 2 power n and Tn is greater than equal to 2 power n by 2. In that case, theta is not possible. Okay. So you will say theta not possible. So what is the time complexity? You can say the time complexity is, you can say the Tn, the time complexity is because of lesser than equal to order of 2 power n, or maybe you can say because of greater than equal to big omega of 2 power n by 2. So both are the correct answer. Either you say this, but theta is not possible. Okay, theta not possible. Understood? So if options are like this, see, if Tn, they say Tn equal to Tn minus 1 plus Tn minus 2 plus 1. So they say option A, option B, option C, option D. If they say something like this, that Tn equal to order of 2 power n, they say Tn equal to big omega of 2 power n by 2. They say Tn equal to theta of 2 power n. They say Tn equal to theta of 2 power n by 2. So which is the correct options? And it has to be MSQ. Okay, it can't be MCQ. Okay, with these options it can't be MCQ. So what are the correct options here? Is A correct? Yes. Is B correct? Yes. Is C correct? No. C is not correct. Is D correct? No. D is not correct. Okay. So only A and B are correct. Tn is not theta. You can't write Tn as theta. Okay. Tn is not theta here. Hope you understood. Right? Okay. Okay. Now see, this was the question, right? Now, as I told you, you can approximate this also, right? I mean, you can say that here, if you write this as lower terms, which means this is the lower term, right? And then if you write it something like this, then what is the answer that you will be getting? Basically, it will be greater than equal to, it is lesser than equal to. Then what is the answer that you will be getting? Okay, if you do some shortcut here, if you replace like this, then here you will be getting, this is n minus 2, right? So Tn minus 2 will be, you can use the substitution method. Tn minus 2 will be 2 into Tn minus 2 will be Tn minus 4 plus 2 or something like this, right? So maybe you can try. Most probably it will be 2 power n by 2. This will be 2 power n. Okay, so you can try like this also. Understood? So here Tn will be lesser than equal to something like this, because this will be 1 plus 2 plus and so on, right? So most probably it will be 2 power n. See, you can just solve it. It will be just increasing GP, right? See here, it will be like this, that it is 1 plus 2 square till 2 power n, right? So it will be 2 power n. So you can use these things also. Okay, instead of tree method, you can use these things also. Let me know if you have understood. Okay, let me know if that is fine to everyone. Okay, so I hope you understood, right? Great. Now, can you solve this as a using a tree method? Maybe you can quickly solve. Okay, you can solve this as an homework. Now let me just give you a hint that how you can solve this. Okay, and then you can solve this as a homework. So see here, the multiple branches are there, but don't worry about this. Okay, you can say that this is n, which you are dividing into n by 2, n by 3, and then n by 4. So this is the branch which will go early terminate. This is the branch which will go at last terminate, right? So can you tell me what are the labels here? Log base 2n, what are the labels here? Log base 4n, right? And then at each node we are doing order of 1 work, right? So here we are doing order of 1 work. So this is 1, this is also 1, this is 1, this is 1, right? So this is ultimately 1, this is 3. Similarly, there will be 3 square work, okay? 3 square work here. So if you notice, this will be 1 plus 3 square, then 3 power k. Okay, this will be Tn. Now for the left branch, what is this k? See, ultimately this will be theta of 3 power k, right? Because this is increasing GP. Since it is increasing GP, don't need to worry about it. So this is the answer, right? But okay, let me just write 3 power k. But now the k here is log base 2n and here is log base 4n. So you will say from the left branch you are getting lesser than equal to log 3 power k, right? 3 power k, and here you are getting 3 power k. And what is the value of k? The value of k is basically log base 2n, here log base 4n. Okay, now since see, it is in the power. Okay, it is in the power. You can't again write the theta because you can do one thing. See, if you remember, then we can rewrite it n power log base 2 3, which means you can exchange this, right? You can exchange this. Do you remember this log property? You can definitely exchange this, right? Now this is saying Tn is lesser than equal to n log base 2 3. This is saying Tn is greater than equal to n log base 4 3, right? Log base 4 3. So since these two terms are different, this function and this function is not same, right? I mean, this will be some number which is greater than 1. This is some number which is lesser than 1, because if it is 4, then only it is 1. If it is 4 squared, then it is 2. If it is 3, then it is lesser than 1, right? If it is 3, then it is already greater than 1. So you can't write theta again. Okay, we cannot write theta again here. Okay, so theta not possible. Okay, so what are the answers? You can say the answers here are, okay, I have already solved it. I thought that I will be giving you as an homework, but anyway, let's just solve it. So the answers here are, you can say theta is T of n is big omega of n is power log base 2 3. Okay, because sorry, not big omega, this is big O, because this is lesser than equal to, so this is big O of this. Tn is big omega, here you will write big omega of n is power log base 4 3. Right? So that's how you can solve. This is also correct, this is also correct. Okay, both are correct. Now let's just solve this last question using the tree method. Can you solve this? Can you solve this question? Okay, from here we will motivate our master's theorem. From here we will motivate the master's theorem. So let's just solve this quickly. See how to solve this. You will say that there is a n which you are dividing into a Tn by b, which means see here, this is n by b, this is n by b, this is also n by b, and ultimately there are a such n by b's, right? N by b. And how many such n by b's are there? There are a such n by b. So I can say these all are a. a and y beach. Is this okay to everyone? Again you will be dividing into a and y beach and so on, right? So ultimately this will be n upon this will be n upon b square and n upon b power k, right? N upon b power k. Okay, so ultimately it will be n upon b power k. In the recurrence relation, if we have more than two functions, yes, it will depend on lesser and higher terms. Yes, so that's how we can solve it. Okay, or using the leftmost and rightmost branch, which means lesser function and the higher function. Okay, yes, that is the correct observation. So can you solve this? See, how many levels are there? How many levels are there? Here the number of levels are, you will say log base b, because you are dividing by b, and log base b n, right? These are the number of levels. At every level, how much work you are doing? At this level, how much work you are doing? At this level, you are saying you are doing c into n power k. At this level, you are doing c into, okay, n upon b power k. Here n upon b power k. And since there are a such things, okay, this is also n upon b power k. Since there are a such things, so a into n upon b power k. Okay, let's not worry about the c. Okay, you can anyway multiply by the c later on, but yeah, a into n upon b power k. So here n upon b power k, here n upon b power k, then a into n upon b power k. Okay, now how much work you are doing at this level? Can anyone tell me? See, this is n upon b square, n upon b square. Okay, n upon b square. If this is n upon b square, so you are doing n upon b square power k. And how many children will be there? If these are the a, then these will be a square, because each one will be having a children. So a square children are there, each of which is n upon b square power k, right? N upon b square power k. Okay, let me know if that is okay to everyone. Right? So basically you will say that in this case you are doing n power k, and then a into n upon b power k, then a square into n upon b square power k, a cube into n upon b cube power k, and so on, right? At the last level, how much you will be doing? See, this is let's suppose that, okay, this k is there. Okay, they have used this k, so maybe I can use something else, right? Maybe I can use p or something, because they have used this name k. Maybe I can use p. Okay, let's suppose this is p, n upon b power p. Okay, so see, they are basically saying n power k at this level, at the first level, n power k. And then each of this, okay, each of this is n upon b power k, n upon b power k, and a such terms are there. So a into n upon b power k, then a square such terms are there, and a square into n upon b square, okay, n upon b square power k, like this, right? Okay. And then ultimately, if there are p such terms, so a power p at the last you will be doing a power p into n upon b power p power k, something like this, right? Okay, something like this. So at the last you are doing something like this. Let me know if that is okay to everyone. Okay, just see this recurrence. This is basically this is going to be the question where we are going to prove, okay, we are going to prove Master's theorem. We are going to prove Master's theorem using this particular recurrence. Okay, using this particular recurrence. I mean, the idea will be clear at least to you. First, let me know if that is fine, if this particular recurrence is fine to everyone. Okay, is this fine? That is how we will be doing it, right? Okay. So at the next level, you are doing a into So it is n upon b power k, n upon b power k. So a into n upon b power k. This is whole power, okay? So a into n upon b power k. Yeah. So this is a into n upon b power k. Okay. Now, do you observe something here? Let's take n power k common if you want. Okay, let's take n power k common. This is 1 plus a upon b power k plus a square upon how to write it clearly. Okay, should it be, see, so let me write it little more clearly. Let me first check if that is fine. See, here we have a square terms, and then each of this will be doing n upon b square, right? N upon b square power k. Okay, so here you will be getting a square into n upon b square. So n power k we have already taken common. So a square upon you can say b square power k, right? Yeah. So b square power k plus a cube upon b cube power k, something like this, right? Okay. So you can understand that it is just like a GP, right? So what is the term here for the GP? What is the term? I mean the recurrence. Sorry, the common ratio. What is the common ratio here? This is going to be the common ratio, right? This is going to be the common ratio. Now see, this is the GP that we have got. Okay, this is the GP that we have got. Now from here you can say that this common ratio, okay, the common ratio is a upon b power k. If this common ratio is lesser than 1, then it will be the decreasing GP, right? It will be the decreasing GP. Now if this is lesser than 1, the common ratio is lesser than 1, then it is a decreasing GP. If this common ratio is greater than 1, then it is going to be the increasing GP. If this is equal to 1, if the common ratio is equal to 1, then this is not going to be a GP. Then you will say then this is just 1, right? Okay, so if there are, let's suppose, p terms or something like that, then it will not be a GP. Everything will be 1, right? Every term will be 1. Okay, cool. So if this is the case, if this is a decreasing GP, then can you tell me what is the answer? If this is decreasing GP, then this Tn, okay, if this is Tn, then what is the answer for Tn? Just n power k, right? So if this is decreasing GP, then this Tn is nothing but n power k. So basically here in this case Tn will be n power k. If this is increasing GP, then the last term, whatever is the last term, then Tn will be n power k into, let's suppose I am saying there are p such terms or x some terms. So if there are p such terms, then a power p upon b power p power k, right? Something like this. If there are p such terms, okay. So what is the value of p? How many terms will be there? How many levels will be there? I think log base bn, right? Log base bn. Okay, so we can definitely solve it. So see here, let me tell you here only. So here, if this is increasing GP, then this will be the answer, right? This will be the answer. And in this case, in case of increasing GP, you can definitely simplify this further on. Okay, I think I made it a little complicated, but let me just finish it. So now you can simplify this further on. So this b power p, what it will be? It will be, you just see here, the p is, I'm assuming, number of levels. So log base bn, right? So it is b of log base bn. It is nothing but n. Okay. So in this case, if it is increasing GP, then in this case Tn equal to n power k into a power, okay, what is a power p? it is a power log base bn, which is nothing but n power log base ba. Okay, so you can write it a power ph n power log base ba, n power log base ba divided by this b power p is n, so n power k. So nothing, it will be nothing but n power log base ba. Okay, n power log base ba. So what I'm saying that in case of increasing GP, it is n power log base ba. Okay, I'm just simplifying this term further on. It will be n power log base ba. And if every term is 1, then how many such terms are here? P terms, which is log base b n, right? So n power, so it is n power k into p terms, so which means log base b, log base bn. Okay. So isn't it the Master's theorem? Tell me. Isn't it the Master's theorem? So in the Master's theorem, if you remember, then this is how the Master's theorem has been derived, right? Okay. This is how Master's theorem has been derived. Let me know if that is okay to everyone. See what I'm saying. Let me just quickly tell you that what I'm saying here. That let's suppose you want to solve something like this, right? You want to solve something like this. Suppose you want to solve something like this. Okay. Then I'm just proving the Master's theorem using this example. How? Let me just quickly tell you again. I'm saying, let me do one thing. I'm saying that we are having n, we are dividing it into a parts, n by b, and so on, right? And so on. So n by b. How many such parts are here? A parts. Okay. A parts. Is this fine? Now we are dividing it further into a parts. We are dividing this further into a parts, this further into a parts. If this is a, okay, if this is a, this is a, this is a, then how many such terms will be here? A square. Okay. Okay. So this will be n upon b square, and then we are ultimately saying this is n upon b power b square. This is something, right? B power, generally we write k, but here instead of writing k, because k has been used, I'm writing b power p. Okay. So at this level the work done is n power k. At this level, this is n upon b power k, and a such terms are here, so a into n upon b power k. At this level n upon b square power k, and a square such terms are here, so n upon b square power k, right? And ultimately, so whatever the number of terms, let's suppose p, so n upon b power p power k, right? Now if you add all of this, okay, if you add all of this, you will be getting the answer. Now if I'm adding all of this, then it depends that if it is increasing GP, I will be taking the last term. Okay. If it is decreasing GP, I will be taking the first term. If it is increasing GP, I will be taking the last term. If it is equal to 1, if every term is equal to 1, okay, then every term is just 1. So if it is decreasing GP, I will say it is n power k, the first term. If it is increasing GP, what is the last term? Can anyone tell me? It will be just, okay, it will be this one. The last term is coming out to be n power log base ba. Okay. So if it is increasing GP, this is the last term. If it is decreasing GP, the first term will be this. If it is everything is 1, then this. So that's how we also prove the Master's theorem. Okay. I mean, in the Master's theorem, we use a general function, but the idea should be clear to everyone. So here I have just used n power k, but in the Master's theorem, we use a general function. Okay. Cool. So general function means fn. Now let's just see the Master's theorem directly. Okay. So Master's theorem has different cases. Let me just tell you what are those cases. See, what the Master's theorem says, that if you have this Tn equal to something, if you have something like this, then what you will do? You will say this Tn can be solved. Okay, this Tn can be solved using the Master's theorem. If the format is like this, okay, here this fn is a function of n, and this is a recurrence, right? Okay. Now what we will do, we will compare between fn and n is power log base ba. Okay, log base ba and fn. We will compare these two functions. If this is greater, then this is the answer. Okay. If this is polynomial greater, what is polynomially? I will tell you. Then in that case, Tn is n is power, so theta. Okay, theta of n is power log base ba. Okay. In this case, okay, if this is greater, then Tn is, in this case, theta of fn. If both are equal, basically if both of these are equal, then what is tn? tn is you need to multiply by the log n, right? N is power log base ba into log n. Okay, tn is this theta of this, right? So see here, earlier also we have got something like this, right? Earlier also we have got, if both are equal, so basically if this is equal, we will multiplying by the log. If this is greater, okay, so we will see that, okay, n power log base ba is answer, otherwise the function is answer. Okay. Anyway, so let's not go to the proof again and again, but I hope this is okay to everyone. Now, should we solve the questions? Let's just quickly solve the question. This is question number 14, and let's just try solving it. So what they are saying? They are saying that this is basically the recurrence that you want to solve. Now, what you will do? You will write the function on the left side. What is the function here? And n is power log base b. What is the b? This is 3, right? This is 3 and a. Okay. So see, this is log base ba. Log base ba. Okay. This is b. This is b. This is a. So the function is n. This is n is power square. So what is greater? This n square is greater, right? Since n square is greater, so that's why you can directly say that Tn is theta of n square. Okay. You can directly say Tn is theta of n square. Now let's just see more things. So here the function is n is power log base ba. So the function is n log n. And now n is power log base. What is the log base? This is b is 4, a is 3, right? Okay. This is going to be interesting. See, this is n log n. This is n is power log base 4, 3. Tell me this power is lesser than 1 or greater than 1. Whenever you have n is power something, just tell me it will matter on the power. It is lesser than 1, right? Because if you write 4 here, then it is 1. If you write more than 4, it is more than 1. If you write lesser than 4, it will be lesser than 1, right? So this is lesser than 1. So this quantity is definitely lesser than 1. Okay. So this quantity is lesser than 1. So that's why you will say, since this quantity is lesser than 1, so that's why you will say that this is, let's suppose this is 0.7 or something. Okay. And this is n log n. So which one is greater? Obviously n log n is greater. So that is why your answer will be theta of n log n. Okay. Whichever is greater, you write that answer. That has to be polynomial time greater. I will tell you what does this polynomial time mean. Okay. Okay. Currently you understand this, that okay, this is greater. So that's why this is the answer. Let's just solve this. What is fn? What is n is power log base b a? Just write both of this. What is fn? This is n log n. What is n is power log base b? Log base b is 2. This is also 2. So this is n log n. Okay. Now this is interesting. See here, is this greater? Actually asymptotically, yes. Asymptotically you are right. But there is something called polynomial time. Okay. This is not a polynomial time greater. Let me now tell you what does this polynomial time greater mean. It means, let's suppose this is n log n. It means that this function, this if you this cancel out n and n, this will be log n. This is just 1. So it has to be, this function has to be greater, but not just greater. It has to be n is power something greater. Is this n is power something greater? No. This is just log n greater. So that's why it is not a polynomial time greater. Okay. See, if I just ask you n cube and n square, is this polynomial time greater? Is this greater polynomially? Polynomially? Yes. Why? Because if you even cancel out, this will be n, this will be 1. So here n is power something time greater, right? It is n is power something time greater. That's why it is polynomially greater. Okay. Now tell me, is this polynomially greater? Is this n is power 2 log n and n? Is this polynomially greater? Just tell me. See, it is greater. And it is also polynomially greater because it is at least n is power something greater, right? In multiply, whatever you have doesn't matter, but it is polynomially greater. So that's why it is polynomially greater. Okay. Now tell me, is this polynomially greater? N square divided by log n and n. Okay. Just tell me, is this polynomially greater? See here, this function n square divided by log n and this is n. Are these polynomially? Is this relation polynomially greater or lesser? What do you think? So here the answer is again the answer is yes. Why? Let me just tell you. See here, you will just cancel out this n and then and then this will be n upon log n. Now see, let me just go to the next page. This is n square upon log n, right? And this is just n. Now even if you cancel out, this will be n upon log n. This is 1. Now here I told you that in the previous video also I told you that this n upon log n, right? In this n upon log n, basically here this n is n power epsilon is far greater than log n power anything, right? Log n power anything. Even this is 10,000, 10 crore, 10 lakh or whatever, right? So n is power any positive power greater than 0. Okay, any positive power is actually far greater than this log n. So basically, let me write it like this. See, this log n can be handled by this n is power 0.1, right? This log n can be handled by this n power 0.1. Basically, there will be n is power something by which it is greater, right? By which it is greater, right? So that is why you will say it is also polynomially time greater. Why? Because there is something n is power something which will remain by which it is greater. So that's why it is polynomially time greater. Tell me. Is this function which is n upon log n, and let's suppose this is log n, is this polynomially greater? Tell me, is this polynomially greater than this function? What do you think? See here, this again, this n is too powerful than log n, right? This 0.1, even if you write 0.1, or maybe this 0.000000000000001 is also too powerful than log n. Okay, which means even if you write like this, n is power, okay, I mean this is 0.99999 whatever, right? So even if you write like this, this log n can be handled by some small very fraction power, and then again this log n that can also be handled by some small power. So basically what I'm saying is like this. See, okay, or maybe if you want, you can divide by the log n both sides, and then you will be getting something like this. See, you will be getting n upon log n square, and then this is 1. So here this log n square, any log n power can be handled by n is power 0.1 only. Okay, this log n square, and then this is n is power 0.99 is remaining. So obviously something n is power will remain. So that's why it is also polynomially greater. Okay, this is also polynomially greater. Understood? Let me know if you have understood. So this is also polynomially greater. Okay. Now tell me, is this polynomially greater? And let's suppose I ask you 2 power n, and then I ask you n only. Okay. Let's suppose I ask you this. Is this polynomially greater? Asymptotically I know. Is this polynomially greater? See, if you're getting something like this, and then you can't cancel out the common terms or something, right? Then what you can do, you can introduce some in between. See, this is n, this is n square, this is 2 power n, right? As we know, this is at least polynomially greater. This is polynomially greater, right? And anyway, this is asymptotically or polynomially, doesn't matter. It is anyway greater. So by transitivity, you can say this is polynomially greater. Okay. See, I can tell you the formal definition of polynomial greater. Don't worry about it. I will tell you the formal definition of polynomial greater also. But for now, understand this, that if you want to compare two functions, if you can't compare directly, then just see if you can introduce something in between. If this is polynomially greater, then obviously this is polynomially greater. So by transitivity, you can say this is polynomially greater. Okay. Yes. Okay. Understood. So that is why these two are polynomially greater. Tell me, is this, let's suppose I ask you, this n and n factorial, is this polynomially greater? Obviously, yes. Why? Even n square is polynomially greater. Then why not n factorial? By transitivity, you can say this is also polynomially greater. Okay. And what is the formal definition of polynomially greater? Let me just tell you. See, the formal definition is in the Masters theorem statement itself. Okay. So they say a function. Okay. Let me just tell you the formal definition, although it might not be too much required, but let's just quickly discuss the formal definition also. This is the Masters theorem formal statement. So they say this fn should be lesser than equal to ns power log base b a, and not just this into ns power epsilon. So they are saying it should be lesser than equal to this. If that is the case, then sorry, greater than equal to, this is big omega, so this is greater than equal to. So if that is the case, which means fn is not just greater than equal to this, it is actually greater than equal to into this also, some ns power also, then this is called polynomially greater. Okay, basically if you even compare, let's suppose if you even compare 2 power n, and suppose you compare 2 power n and n. Okay, so tell me, is this 2 power n is polynomially greater than n? Can you say this 2 power n is not just greater, okay, is not just greater than equal to, it is also basically ns power, even if you add something, okay, maybe 0.1, if you some fraction also, okay, is this polynomially greater? Then yes, obviously it is. Even that's why I said, like, you can introduce some function in between, right, which is n square. So it is greater than equal to n square, so that's why it is greater, right? So that's why I said you can introduce some function in between. Anyway, don't worry about the formal definition. I've shown you the formal definition, but don't need to worry about it. Okay. Okay. Tell me, is this ns power 0.1 polynomially greater than ns power, let's suppose 0.001? Is this polynomially greater? Yes. Because this is ns power something greater, right? It should be ns power something greater. So hence these two are polynomially greater. Okay. Tell me, is this polynomially greater? N log n and n. Is this polynomially greater? No. This is asymptotically greater, but not polynomially. Okay. So the Master's theorem wants you to be polynomially greater. This is not polynomially greater. This is asymptotically yes. Yes, but polynomially no. Okay. Because even if you cancel out, then this is just log n greater, not n is power something. Okay. So it is not polynomially greater. Right? Now tell me, maybe any other thing. Um, okay. Maybe you tell me this n log n and n is power log n. Tell me, is this polynomially greater? See, if you cancel out this, then this is log n square greater, right? This is log n square greater than 1, which is not a polynomially greater. So polynomially, no. Okay, polynomially, no. Right? Polynomially, no. Okay. And asymptotically, yes. Okay. Asymptotically, yes. So I hope now you understood that these two functions are just log n greater. Now there is a Master's theorem which says, the Master's theorem says, if both are just log n greater, then the final answer will be theta of n log n into log n. Okay, the final answer will be just whatever is a greater into log n. If this is just log n greater, okay, just one time log n greater. Okay, so that's the Master's theorem which says that okay, if they're equal, then multiply by log n. If that is the case, that if this term is just one time log n greater, then you can multiply by the log n also. Okay, so we will see that, don't worry. So let me just go to that example. Okay, so can you tell me in this, what is the fn? What is n is power log base b a? See, fn is n square, n is power log base b is 2 and then 8. This is n cube. So what you can say here, just tell me which one, what is the answer? Can you tell me the answer in terms of the theta? What is the answer here? Let me know. See, which term is greater? You just need to tell me which term is greater, and based on that, you can get the answer, right? Okay, n cube, right? N cube is the answer. Theta of n cube. Yes. So that was the easy question. Now let's just go to the next question. Okay, n cube is the answer. Great. Now let's just go to the next question. So tell me what is the answer here? What is Fn? What is Fn and what is ns power log base b a? So Fn is square root of n and ns power log base b. What is the log base b? Log base b is so this is a, the b is 2, right? Okay. So this is 0. So this is 1 and this is square root of n. Is this polynomially greater? Tell me. Is this polynomially greater? Yes, right? Since it is greater and even the polynomially greater, so that's why this is the answer. Now tell me this. What is Fn? What is ns power log base b a? What are these? Fn is n cube log n, right? And ns power log base b, log base b is basically 2 and this is 4, right? So this is n square n cube log n. Is this greater? Yes. So n cube log n is the answer. Okay. Similarly, let's just solve this question. What is this Fn? What is ns power log base b a? So Fn is n square. This is ns power log base b is 2, 4. This is also n square. Are these polynomially greater? Is this polynomially greater? Since no, so we cannot, currently we are saying we cannot apply Master's theorem. Okay. Okay. If it is not polynomially greater, let's say that we cannot apply Master's theorem. We will see that how to solve. Okay. Because it is not polynomially greater. So this is, see, this is n square and this is going to be n square again, right? Okay, so both are n square. So let's just see here in the Master's theorem, what do we have? See, if it is polynomially greater, then we directly know. Now in the Master's theorem, there is a the second condition which says that if both are actually equal, then you can just multiply by the log n. Okay, so in this case, if both are equal, right? If both are equal, then we will say that okay, we can apply. Actually, I have just written it purposefully just to let you know that we can apply that. What is the answer? If both are equal, then the answer will be theta of n square log n, right? N square log n. Yes, we can apply. Okay, understood. Now let's just solve more questions. Now tell me here, the function is 2 power n and n is power log base b a. What is this? Log base b is 2, 1. This is just 1. Is 2 power n polynomially greater than 1? Yes. So theta of 2 power n is answer. Okay. Theta of 2 power n is answer. Let's just solve this. This is log n square. This is log base b. N is power log base b a. Tell me, is this term greater than 1 or lesser than 1? Definitely lesser than 1, right? This is n is power 0 point something, right? 0 point, let's suppose 7. Okay. I don't know, but it is 7. Yeah, this is interesting. Tell me, is this polynomially greater? Is this polynomially greater? This is very interesting question. Tell me, is this polynomially greater? See, n is power even 0.001 can handle this, right? Can handle anything, okay? Can handle log n power anything. So that's why the remaining will be there, right? So that's why you will say it is polynomially greater, right? So that's why theta of n is power 0.7 is answer. Okay, theta of n is power 0.7 is answer, right? Great. Now just tell me this. Okay, this is the same question. Now just tell me this. This is Fn is, yeah, this is theta, right? Okay, so this is n log n only. And what is n is power log base b? Base b is basically 2, age 4. This is n square. This is n log n. Is this polynomially greater? If one of them is polynomially greater? Yes, right? So that's why theta of n square is answer. That's why theta of n square is answer. Okay. Now tell me this. See, in the Master's theorem, we have seen three cases, right? There are three cases. What is one case? If both are equal. Sorry, let me go like this. If fn and n is power log base ba, if this is the relation, or this is the relation, or this is the relation. In this case, theta of fn is answer. In this case, theta of n is power log base ba is answer. In this case, if both are equal, the third case is if both are equal, then we can multiply by the log n, theta of log n into fn, or whatever you want to write, n is power log base ba, because both are equal, right? Okay. So these are the three cases. But let's just see a generalized Masters theorem which has even more cases. Okay. So the generalized Masters theorem says it is basically saying that if one of them is basically see it is saying, let's just have fn and n is power log base ba. It is saying if this is greater than earlier, okay. If this is greater earlier, okay. Equal also okay. But it is saying, let's not even worry about the polynomial thing. Okay. It is saying even if it is not equal, if one of them is log n times greater, okay, which means let's suppose that fn and this is n is power log base ba. If let's suppose this is n square log n, this is n square only. Okay, if one of them is basically log n times greater, okay, it is a slightly different condition which is saying if one of them is n log n times greater, then what you can do, you can directly write the answer here in such a way that log n square, okay, log n square. Basically it is saying that if one of them, if let's suppose that if fn is basically log k, okay, log k n in multiply by log k n, which means this term multiply by log k n, then your answer will be log k plus 1. Your answer will be log k plus 1. Which means if fn is basically like this, if one of them is log n times greater, then your answer will be you need to multiply by one more log n. Okay. I mean, this fn is log n times greater, then also you can do it. I mean, we can prove it, but that's not need to prove. In the course, we have given the intuition for the proof. Okay, for every of this theorem, we have given the intuition. So anyway, let's just quickly solve this. Okay, let's just quickly solve this. So what is fn? Fn is n log n, and what is n is power log base ba? This is just n. So see here, this is greater and log n times greater. Then we can still write the answer directly. Okay, instead of solving using any other method, we can say it is n log n into one more time log n. Okay, which means n log n square. Okay, is this understood? This is the generalized Masters theorem. And why do we even have the Masters theorem? Why do we even have the Masters theorem and so on? Because these are the recurrence relations. See, this recurrence relation, any of this of form recurrence relation, a t n y b plus some fn. These recurrence relations are so common that people are saying, let's just solve it at once. Okay, so people are saying solve it once and keep using the theorem, keep using the formula, right? The result. Okay, so that's why we have it. Now what is fn? Fn is n into log n power 10, and here it is just n. So since it is log n times something greater, so that's why also you can directly write the answer theta of you need to multiply one more log n. So which means it will be power 11 is the answer. Okay. Now tell me this. See here, the fn is this, and this is this, right? This is this. The fn is this, and this is this. So how to solve this? Tell me. So here fn is basically, we are saying here it is in the division, right? It is not in the multiplication. So earlier it was in multiplication, now it is in the division. Don't worry, I will summarize everything. So here, to solve these kind of questions also, we have one theorem which is called extended Masters theorem. Okay, so here, I mean, I think in the GATE they have not asked the questions where this fn is, see, this fn is let's suppose this fn is n square and n square log n and this is just n square, right? N is power log base ba is just n square. Then we know the answer using the generalized Masters theorem, which is theta of you need to multiply with the log n. Okay, so log n into n square log n, right? You need to multiply using generalized. We can answer. But there is something called extended, which says that even if it is in the division, okay, even if this log n in the division, okay, then also we can answer. If this is the division, then also people have solved it. Okay, the people have solved it, the generalized forms, right? So if it's division of any power, okay, maybe the power 1, power 2, then also people have said that, okay, so some answer is there. People have solved it and they are saying that you can directly use the formula. So what is that? People are saying that, see, earlier we were just having these two cases. If it is just log n multiplication, then it will be +1. Okay. Now we are also having more cases in the extended Masters theorem, which is saying even if it is division, now in division also, if it is just one time division, okay, one time division, then it is log n. Okay, if it is just one time division, it is log n. If it is more time division, then it is just this function. So let me just tell you what they are saying. Let me just summarize all about the Masters theorem. Okay. Let me just summarize this. Okay. So summary. What I'm trying to say, and then we will see more examples. Any Masters theorem or all about all cases of Masters theorem. So one case is that this is Fn, this is n is power log base ba. Okay. One case is that this is, let's suppose, okay, this is, let's suppose, n square. Okay, this is, let's suppose, n square. This is n. I mean, if it is strictly greater or strictly lesser, then you know theta of n square is the answer. Okay, so let me go to the next page. Basically, if this is Fn and this is n is power log base ba. Okay, now let me just tell you, if it is n square, this is, let's suppose, n. Okay, then what is the answer that you know, right? What is the answer? Theta of n square. Great. If this is even, let's suppose n log n only, this is n, then also we know if it is just log n times greater also, then also I think we know this is n log n into log n, right? Let's suppose if it is n log n square into n, then also I think you know this is n log n over q, right? So these cases that we know. If both are equal, then do you know? If both are equal, then if this is n, this is also n, then this is theta of n log n. Okay, both are equal, then you know. If it is multiple of log n only, then you know, right? If it is polynomially greater, then you know. But there is one more case that extended has added. It is saying, just see here, it is saying that if it is n divided by log n also, okay, and this is just, let's suppose this is n square and this is n square, it is like that. Okay, then in that case, let me just go like this. Okay, so it is saying that in that case the answer is, let's just see the answer here. See here, if it is division, okay, one time division, then answer is this n log base ba into log n. Basically it is saying if it is one time division, then theta of n square into log n. Okay, if it is multiple time division, n square divided by log n power 3 or 2 or whatever, right? Power any other power 3, 2 or anything, and this is just n square. If this is multiple time division, then the answer is just n square. Okay, so these are the all cases. So see, I hope that these cases that you know, right? Even if you remove these cases, at least these cases you know, these things you know, right? I hope these things you know. If this is greater, then this is the answer. If this is log n times greater, then just multiply by log n multiple times. Okay, both are equal, then log n. These are the Masters theorem. Now they have added these cases also in case of extended, like these are the extra conditions that you, if you want, you can remember. Okay, they are saying that people have got these kind of patterns, so that's why they have solved these also as upfront. Okay, so that's called extended. If you want, you can remember, otherwise you can leave it. Okay, but yeah, that's also that is the thing that you should definitely know. You should know. Okay, you should know. But if you want, you can remember the extended also. Is this fine to everyone? Okay. Okay, so this is what you should know. In extended, if division by log n, you might remember or you might not remember. Okay, division by log n. Multiplication by log n, I hope you know. Okay, so let's just do one or two practice. Let's suppose this is n square. This is let's suppose n. Then what is the answer? Then in that case, this is fn. Okay, this is n's power log base ba. Okay, in that case, what is the answer? Then answer is n square, theta of n square. Let's suppose this is n log n. This is n. What is the answer? This is log n times greater. So n log n into log n, right? N log n into log n. Okay. If let's suppose this is n, this is n, what is the answer? Theta of n log n. If let's suppose this is n square log n and this is just n square, then what is the answer? Theta of n square log n into log n, right? Into log n. So in multiplication of log n, you know. If both are equal, then also you know, right? If this is greater, then also you know. But there is one extra condition that they are adding. If you by the division of log n, right? If you remember that is okay. If you don't remember, that is also okay. Which means they are saying, let's suppose it is n square by log n. Okay, and it is just n square. In that case, this is n square log n. Okay. If it is multiple divisions, which means if it is saying let's suppose it is saying that n square divided by log n, also multiple division, let's suppose 3, and this is n square, then just n square. Okay, just n square. Basically it has decreased so much that you won't consider it. Okay, it is basically decreased little bit, so that's why the answer will be little bit consideration. Okay, understood. So now let's just move to the next question. Let's just see this. So what is this? What is fn? And what is n's power log base ba? What is fn? This is n square divided by log n whole square. And what is log base ba? This is n's power log base b and 4, which is n square. So here you have n square and here you have n square division by now it is division by log n, right? Now it is division by log n. So if it is multiple divisions, then you know the answer. What is the answer here? This is theta of n square only. Okay, theta of n square only, right? Now let's see this. This is fn. Okay, write the fn on the left part. Okay, just for the sake of consistency, fn I always write on the left. Okay, now this is n log n square. This is n power log, what is log base b? 3, right? 9, which is n square. This is n square. So this is n square log n square. This is just n square. So which is greater? This is greater, but not polynomially. That's okay. But it is log n square greater, right? So what is the answer? Theta of, it is not division. It is multiplication. So log n power cube, right? Okay. Now tell me this. This is fn. This is log base ba. N power log base ba. Right? So what is fn? N power n upon log n cube. This is n only, right? Okay, sorry, n log base 2. So yeah, this is n only. So this is basically log n. I mean, this is division. In case of division, if it is multiple divisions, then theta of n only. Okay, theta of n only. If it is multiple divisions, then theta of n only. Okay. Okay. Now you have to solve this. Okay, I'm not going to solve this. You only tell me what is the answer. This is fn. This is n's power log base ba. So this is log base b is 2, and which is n square. This is n upon log n square. Yeah, this is interesting. Can you tell me? What is the answer? What is the answer? See here you need to tell me the answer. This is little interesting question. First of all, tell me this polynomially greater. Is this polynomially greater? What do you think? I think yes, right? I think yes. So this is the polynomially greater, because even if you multiply log n squares, then it will be definitely polynomially greater. So theta of n square directly answer. Okay, theta of n square is directly answer. Okay. Now you tell me this. Okay, I'm not going to solve this. You tell me this. This is fn. This is ns power log base b. What is log base b? It is basically 4, and then this is 16, which is ns power 4. So fn is n square. This is ns power 4. What is the answer? What is the answer? Just tell me. Obviously ns power 4, right? Directly. Ns power 4 directly. Right? Can you tell me this? Fn and ns power log base b. Log base b is 2, a is 1. So this is 1, this is also 1. Yeah, this is interesting. Can you tell me the answer? Both are 1, both are same. If both are same, then what is the answer? Any function you take 1 into and then log n, right? So this is the log n. Have you seen this kind of recurrence before? If you know about the binary search, then this is related to binary search recurrence. Right? Binary search recurrence. Okay. So see here. Okay. Was there any confusion here? Why n square log n? Okay. Let me see. Okay. So in this question, n is answer, right? Cool. Now let's just solve this question, which has been asked in GATE 2021. What they are saying? They are saying, okay, by the way, in the Masters theorem also, a is greater than or equal to 1 and b is greater than 1. This is some condition. Anyway, let's not worry about it. So they are saying that which of the following options is correct. So this is I think MSQ or MCQ. Okay, this is MCQ only. Okay. So let's just see. Maybe I can go to the next page and then try seeing all of these options, and let's just see what is the correct answer here, right? Okay. So if fn is, now they are saying fn and n is power log base b a. Okay. They are saying if fn is n log n, if this is n log n, then tn is on log n. Do you think? No, it will depend on this, right? A and b. It will depend on a and b. They have not given the values of a and b. Then it is n log n. No, I don't know. It will depend. Right? So A is a wrong answer. A is wrong because it will depend on the value of A and B. Now, can you tell me, is B is correct or B is also wrong? So A is wrong. What about B? Let's just talk about B. Okay. So they are saying if fn is this one, and divided by log n, then just log n is the answer. Okay. What do you think? If it is division, then also it will depend on this, right? If this is just 10, if this is just 10, then what is the answer? See, just tell me this. Okay, if this is fn, this is ns power log base ba. If this is n upon log n, okay, if this is n upon log n, and now let's have the cases here. If this is n, then what is the answer? If this is, let's suppose, n log n, then what is the answer? If this is just log n, then what is the answer? Can you tell me the answers here? If this is n, since it is one time division only, that is why n log n is the answer. Now here this is n upon log n, and this is n log n. Okay, so can you tell me what is the answer? Can you apply the Masters theorem here? I think this is neither, I mean, one of the function, as you can see, one of the function neither is the polynomially time greater, right? This is not the polynomial time greater. Neither you can say that this is not a polynomial time greater, first of all. Okay, now because if you even cancel out n and n, then it is not a polynomial time greater, right? Neither it is just a divide by log n or multiply by the log n, right? So it is not the case of anything. So can't apply Masters theorem, right? Can't apply. Okay, because okay, is this correct? You can't apply, or there is something we can do. see this function is definitely this function you can write it n log n divided by log n square, isn't it? Right? So basically you can say, okay, first of all, I'm sorry about it, this function can't be in the form of log n, right? Okay, so these cases are not a very good cases. Anyway, so these two cases I should be taking things in the power of n only, because this function, this thing should be in the power of n. Okay, let me take some other case. Let's take this is n square. Now tell me, this is n upon log n. Now tell me, is this polynomially greater? Is this polynomially greater? I think even it is polynomially greater than n. So why not with n upon log n, right? So yes, so theta of n square, right? Theta of n square. Okay. Now you have to take that in the n power something. So let's just take one more example. Let's just take in n power only. Let's just take this as n is power 0.7, and this is n upon log n. So what do you think? What do you think? Is this polynomially greater? Yes, right? See, n upon log n, just tell me n upon log n and n is power 0.7. Which one is polynomially greater? See, this you can write it n is power 0.7 into 0.3, right? N is power 0.3. Actually for this log n, in fact n is power, okay, maybe I hope you are understanding. Maybe you can write n is power 0. Let's suppose 0.2, and so basically what I'm saying that there will be something that will get remain, right? Even if you divide by log n. So basically n is power even 0.1 can handle this, right? And this is n is power 0.9 will remain, and this is n is power 0.7. Obviously this is greater, right? This is polynomially greater. Okay, this is polynomially greater. So in this case, what is the answer? Since this is polynomially greater, that's why theta of n upon log n is answer, right? Theta of n upon log n. Hope you understood. So basically based on polynomially greater or not, you can tell me. Now here this is n log n, and they are not even telling the values of a and b, and then they are directly saying it is log n. I don't think, right? So it will depend on values of a and b. So if it is let's suppose greater than 1, if it is greater than 1, then this will be the polynomially greater. If this is lesser than 1, then this will be the polynomially greater. So the answer will never be log n, right? See, in case of b, even if I analyze this further, see, this is just a further analysis, okay? I mean, for the question solving, I may not be requiring this, but for the further analysis, I'm saying that log n can never be the answer. This is, see, this fn is, in case of b, I'm solving b, okay? In case of b, if this is n upon log n, now let's have two cases here. This has to be in n power. Let's suppose this is n greater than 1, okay? Maybe n square. Let's suppose n is power 0.7, lesser than 1. In this case, n square is the answer. In this case, n upon log n is the answer, right? If this is lesser than 1, then this will be polynomial greater than 1, then n square is the answer. Log n can never be the answer anyway, okay? So anyway, it depends on the values of a and b, so that's why b is also wrong, a is also wrong, right? So a and b both are wrong. What about c? What do you think? What about c? Let's just talk about the c, okay? C seems to be little interesting. Let's just see what is the c. C is saying that this function is greater than equal to this, right? And they are saying polynomially greater actually. Okay, this is the definition of polynomially greater. They are saying that this function is polynomially greater than this. Then what does this mean? If these two are polynomially greater, then fn is the answer, right? So for epsilon greater than 0, sorry, they are saying minus. Okay. Oh, interestingly, they have put the minus, not the plus. So very nice question, right? So they are saying minus, which means they are saying basically this is greater than equal to something like this, right? Something like this. Sorry. So they are saying this is minus. So not greater. Basically, this is lesser, right? Fn is equal to order of n is power log base ba minus epsilon, right? Which means fn is lesser than equal to n is power log base ba upon ns power epsilon, right? So basically they are saying this is lesser than equal to this, not just this, it is lesser than equal to this also, which means it is polynomially lesser. If this is polynomially lesser, then obviously this is the answer. So theta of this is the answer, right? So that's why C is the correct answer, right? So what about D? See, A is not correct, B is not correct, C is the correct. What about D? Let's just see the D. D is saying if both are equal, then what? If both are equal, then this is not the correct, right? This is not the correct. Then the answer is log n into ns power log base BA. Okay. Okay, I hope you understood. So basically, they have asked very nice question, I think, in GATE 2021 or 22. This is 21 question. This is a very nice question, but I hope you are able to solve this, right? So A and B are straight away reject because it will depend on the relation between A and B. Yeah, A is greater than equal to 1, B is greater than 1. This is not telling whether A is 2 times B or 3 times B or something like that, right? So it will depend on the relation between A and B. So that is why given just Fn, we can't tell you unless and until you tell the relation between A and B. Okay. Cool. Okay. Now let's go to the, so answer is C. Okay. Answer is C. Now, see, in the Master's theorem also, the definitions are very, very clear. In the Master's theorem also, they always write the formal definitions, which means, yeah. So which means they say, it means what? It means what? Fn is lesser than equal to, right? It means Fn is basically polynomially lesser. Okay. It means Fn is polynomially lesser. If it means Fn is polynomially greater. Okay. Now, let's do one thing. Maybe if you want, we can create some variation out of it, right? Okay. So see, this is the Master's theorem that we have, right? Now let's take some question, okay, which is just like a previous question. Let's say that if Fn, okay, maybe I can say something like this. Okay, if Fn is equal to let's suppose I say order of n power log base B A. Okay, then if Fn is this, and they don't tell anything about A and B, okay, then Tn is theta of Fn. Tn is, okay, first of all tell me, is this true or false? True or false? Is this true or false? See here, I am not saying, see, Fn is lesser than this. That's correct, right? But I am not saying how much lesser. Since I'm not telling you it is polynomial lesser or not, so I can't say something, okay? I can't say, okay, let's suppose this option is ns power log base B, okay? I'm just asking you true or false here. I'm just asking you true or false. Then what is your answer? This is ns power log base BA. Is this true or false? This is false, right? This is false. Actually, it is lesser than equal to this. I agree, but it has to be polynomially lesser. So that's why it is false. Okay. You don't know whether it is polynomially lesser or not. Okay. Now suppose they say Fn equal to theta of log n into ns power log base BA. Then what is Tn? Can you tell me Tn? Since it is basically, you can say it is log n times greater. So that's why it will be theta of ns power log base BA into log n square, right? Okay. Okay. I hope you understood. Cool. Now let's see some cases that even Master's theorem can't solve. Okay, there are many things that Master's theorem also can't solve. So see, there are lots of problems that cannot be tackled by Master's theorem. It's great. Master's theorem is great when it applies, and it's useless otherwise. Okay, if you can't apply, then it is basically useless. So there are many cases. For example, there is a case something like this. Okay, which means if this is not constant, then you can't apply the Master's theorem. If b is not constant, then you can't apply the Master's theorem. Okay, if b is log n, then you can't apply the Master's theorem. If a is square root of n, then you can't apply the Master's theorem. Okay, and the third case is, let's see this, that if a is lesser than 1, okay, it has to be actually greater than or equal to 1, then you can't apply. If b, okay, if b is also lesser than 1, then you can't apply, because b has to be greater than 1. So a has to be greater than or equal to 1 and b has to be greater than 1 to apply the Master's theorem. Okay. Now, if this fn is not positive, you can't apply the Master's theorem. Okay. And if this fn, basically there is something called regularity condition. Okay, I'm not going to tell in the detail, but if this is some sine or cos, then you can't apply. Okay, because of there is something called regularity condition. And if a and b, okay, are not fixed, I mean in such cases also you can't apply the Master's theorem, right? Okay. Now let's see a very nice, okay, and cute method. I can say it is a cute method, which is called change of variable. It is not a method by itself. It is basically there to help you in changing the form. Okay, and then we can apply Master's theorem or some other theorem. Let's see this question. Okay, let's see this question. See, can you solve this question using Master's theorem? No, right? Master's theorem you can't solve. Can you solve using the substitution method? Probably, but it will be too tricky. We have solved it, right? We have solved it using the substitution theorem, substitution method, but it was too tricky. But now in this particular question, we are going to apply change of variable method. Okay, let's just see what is this. Let's see step by step. What is the step 1 in the change of variable method? What is the step 1? It says you put n equal to something. Can you put n equal to 2 power something, 2 power m? Because it is a square root, then it will be better, right? This is step 1. Now after this step, what is your tm? T 2 power m equal to, this will be t 2 power m by 2 plus 2 power m by 2, isn't it? Okay. So, or in other words, you can say m is log n. Okay. So either you say this or you say this, both are fine. So this is the step 1. Step 1 is saying that you are putting n as 2 power m. Okay. Step 1 is saying you are putting n as 2 power m. Is this fine? Okay, great. Now let's just see this. Okay, now here either you say n equal to 2 power n, or you say, okay, or you say m equal to log n. Both are actually fine. Okay, anyway, so once you have this, now there's a step 2. What is this step 2? It says that you put this t as some function. Okay, this whole t as some function. So let's just assume this whole t as sm equal to t 2 power m. So what is this? Let me just tell you what is this. See here, that what I'm saying, that whenever you have t of something, okay, t of 2 power m, I'm putting that as sm, which means I'm saying that you take log of this and you put it here, which means let's suppose I ask you what is t of 3 power m. Okay, which means see, let me just go to the next page. If I'm saying if t of 2 power m is sm, then what is t of 3 power m? Let's suppose t of 2 power 2m, okay, 2 power 2m. Then you will say that you just take log of this and you put it here. S equal to log of this. What is log base 2 of this? Is 2m, right? Which means if I just say t of anything if I ask you, then what is this? S of log of that anything, right? Log of that anything. So if I'm saying that, let's just assume that sm equal to t of 2 power m, then what will be this t of 2 power m by 2? You just take the log, right? T of 2 power m by 2 is basically sm by 2. Log base 2, sm by 2. Okay. Now in the step 2, what you will do, you will convert that into the SMs. Now you will say this is nothing but SM equal to Sm by 2, and T of see this 2 power m by 2 should be, you divide by 2 both side, right? I think, okay, sorry, it is already in 2 power, see this is already in 2 power, right? I mean this is already in terms of m, so maybe you can leave it as it is. So plus 2 power m by 2. Let me know if that is fine to everyone. Okay, let me know. See, whatever I have written as in step 1 and step 2, is this fine or there is any confusion? Let me check. Okay, okay. So I hope that is fine, right? Okay. So basically you got it, right? So now you are having Sm equal to Sm by 2 plus 2 power m by 2, right? This is what you are having. Now can you tell me, can you apply the Master's theorem here? The function is 2 power m by 2. This is n power log base b. What is the log base b? It is 2 and then 1. So basically it is just 1. Is this polynomially greater? Yes. So basically you can say Sm is finally theta of 2 power m by 2. Right? But you need the Tn, right? You need Tn. So see here that you have got, let me just write everything on just one page. Okay. So see here that you have got this. You started with this. You said that okay, we will be solving using Sm, and you have got Sm as 2 power m by 2, right? So using the Master's theorem, we have solved. Okay, let me write it here. See, using the Master's theorem, we have solved, and we have got Sm as this. But we want the answer to be for the Tn. So what is the answer for Tn? See, this Sm is nothing but T of 2 power m. So you can write it as T of 2 power m is nothing but theta of 2 power m by 2. But you want in terms of n, right? So 2 power m and n are related like this. So this is nothing but T of n and 2 power m by 2. So it is basically, you can say m is log n, right? Okay. So what is the value of 2 power m by 2? See, if n equal to 2 power m, I am asking what is the value of 2 power m by 2. So what you need to do here, maybe you can use 2 power m by 2 is nothing but 2 power, this is log n, right? Log base 2 n by 2. Okay. Is this okay to everyone? Let me know. That 2 power m by 2 will be something like this. Or maybe I mean you can use this. So basically you can use directly the shortcut. The 2 power m by 2 will be, you just put 1 by 2 power everywhere, right? 1 by 2 1 by 2. So it will be just square root of n, right? It will be just square root of n. Okay, you can power 1 by 2 everywhere. Okay, so basically this is nothing but theta of square root of n. Why? Because t 2 power m, sorry, n is 2 power m. So you put 1 by 2 power both side, then it will be 2 m by 2, which is square root of n. Okay, so final answer is square root of n. I hope you understood. Let me know if there is any problem in understanding this. Maybe let's just do one thing. Maybe let's just solve more questions and you will get to understand more. Okay, because this method is very nice, so we can solve more questions here also. So see, okay, so first of all tell me, if t of 2 power m is Sm, then what is this t of 2 power m by 2? See, you just take log of this, right? And then you are putting s of log of this is m by 2, basically is m by 2. Okay, what is this? This will be s of, you just take log of this quantity, it will be m power k. what is this? This is 2 power m power k, right? Which is nothing but 2 power mk. So this is s of mk, right? What is this? This will be, can you tell me? You just take log of this, s of log of whatever this is, 2 power m divided by k, right? So basically, if someone give you this relation, then can't you tell me any other form? You just take log of this, right? That's how we are defining it. Okay. Now let's solve this question, and now let's just try to solve this using the change of variable method. Okay. See, can you apply Master's theorem directly? No. And any other method will be little ugly. So that's why we are applying the change of variable. What is the step one? You take it as a sum form. So you apply n equal to 2 power m, or in other words, m equal to log n. Okay, whatever you want to say, you can say. Now what is the step 2? So basically, I mean, first you rewrite it, which will be t of 2 power m equal to t of 2 power m by 2 plus log n, right? What is this log n? This will be m only. Okay. Now step 2 says that you assume the function itself, right? So basically now we are going to assume the functions itself, which means we are going to say in step 2. What is the step 2? We are going to say that, see, this is going to be log of, right? This is this is going to be s of m. That is why this is going to be s of m by 2, and this is already m, right? Can you apply the Master's theorem now? Yes, right? This is m power log base ba. So basically it is 1. So theta of m is the answer, right? Sorry, this is theta of m, right? So you can say this is theta of m, right? This is theta of m. Since this is theta of m, now can you solve for Tn directly? So see here, see what we have got is Sm is this, right? So now you see, now Sm is basically theta of m. Now can you write the Sm as something, T of something? Yes, it will be T of 2 power m. This is theta of m only. Now let's just convert this m also. So basically T of 2 power m or is nothing but n, right? Tn. So this is nothing but Tn. M is nothing but log n. So theta of log n. See, we did it directly, right? Very easily we can solve it. Otherwise, using the substitution method and all, it will take a lot of time for this particular question. It will take a lot of time. So that's how we can solve these questions very nicely, very neatly using change of variable method. Okay. So let's see the Stanford question. Okay, for this change of variable method, change of variables, that is the heading. Okay, for this question in the Stanford, I have taken this from the Stanford. Let's just see this question from Stanford, that how to solve this particular question using change of variable method. Okay, so this is a question which I have taken from Stanford. Now let's just try solving it. Now what they are saying, let's just see. See, this is the quantity that we are interested in, right? Okay. So what is the first step one? Let's just assume n to be something. Should we assume, or what should we do? Yeah, let's just assume that to be 2 power m, right? So which means this is t of 2 power m equal to 2 into t of 2 power m by 2 plus, or in other words you can say m equal to log n, right? Plus m, right? Okay. Now let's just assume that to be s of m. So this is s of m equal to 2 of s of m plus m. Now can you solve this using Master's theorem? Tell me. Using Master's theorem, what you will say? This is m. This is m power log base b. Okay. Base. So sorry. Is this correct, or there is something? Yeah. This is m by 2, right? This is m by 2. Sorry about it. So basically a and b are equal. So this is also m. So you can say both are m, right? Both are m. So both are m. So that is why m log m is the answer using the Master's theorem, because both are the same quantity. So you can say we have got Sm equal to m log m. This is the answer we have got using the Master's theorem, right? Tell me, what is this Sm? Sm is t of 2 power m, which is theta of m log m. But I want in terms of n. So this is also n, Tn, right? This is also Tn. And then m is log n. Okay, so see here, this is interesting. This is theta of m is log n, and log of log n again, right? So log n into log of log n is the answer. Okay, see, very neatly we have solved it. Final answer is log n into log of log n. Okay, theta of this, right? Very, very clearly we have solved it. See here, see, this is the answer, right? Yes, yes. So someone is asking that how do we know that we need to apply this method? You can see the complex form, right? Square root or something or something. So these things are not suitable for neither Master's theorem or nor for the substitution method. I mean, substitution method will go very ugly. Okay. So that's how you know that you need to apply this or not, right? See, ultimately we are applying Master's theorem only, but on the neat and clean form, right? We are applying the Master's theorem only, but on the neat and clean form. Now let's just solve this. So let's just do the step one, which is this, right? Or in other words, m is log n, right? And then this will be t of 2m, 2 power m equal to t of 2 power m by 2 plus log n. Now just assume that to be Sm. This is S of m by 2 plus, see, this is log n, so I can put it as m, right? So let me just put it as m, because everything is in m, right? So let's just put it as m. This is m, okay, plus log m. Now can you apply the Master's theorem? This will be log base b, and so this will be, I think, 0. So this is just log m, right? Now using the Master's theorem, you can easily figure out this is log m into log m, right? Log m square. Okay, using the Master's theorem, right? Now can you tell me what is the final answer? See, now you can just tell me the final answer. How? You will say this Sm is nothing but t of 2 power m, which is ultimately nothing but t of n. So this is actually t of n only. Okay, and then theta of log m whole square, and m is nothing but log n. So basically log of n is log n and then whole square, right? So that's how easily you can solve this question. See, log into log n whole square. Okay, answer I have not written on the slide. I mean, the printed answer is not there, but yeah, that's the correct answer. Okay, isn't it very nice, neat and clean method? Let's just solve this. Okay, let's just solve this question also. This is question number 40 in this particular session. So we have solved many questions, right? Till now we have solved ultimately 40. This is the 40th number question, which is too much, I think. Okay, so I think you people are also enjoying solving the questions, right? So let's just solve this question now. Now can you tell me that what is the answer that you will be getting here? See, let's just solve this. This is the question number 40 that we are solving currently, right? Okay, so n is 2 power m. Now this will be t of 2 power m equal to t of 2 power 3 into t of 2 power m by 2 plus 1, right? Now let's just assume that to be Sm 3 into t of Sm by 2. Sorry, this is 3 into m by Sm by 2 plus 1, right? Plus 1. Now can you tell me using the Master's theorem, what will the answer here? Using the Master's theorem, this is 1, this is log base b, this is a into t n by b, right? So 2 3, right? So this is basically greater than 1, right? I mean, this is n power something, so I think this will be the answer. Ultimately this will be the answer. So theta of m power this, right? So theta of this is answer. Now m is nothing but log n, right? Log n. So this is tn only. So you can say from here tn equal to m is nothing but log n. So that's why this is log n power log base 2 3 theta of this, right? See, very easily we have solved this, right? Very easily we have solved this. Let me know if that is fine. Okay, let me know if there is any question till now. Okay. So this is the answer that we have, right? Now let's just solve this. Question. Okay, this question I have again taken from Stack Exchange. Let's just solve this question. See, in this question also we can apply the same tricks, right? We can apply the same tricks. So how to solve this question? Let's just see. Here they are saying this is the question, right? Now this is the 41 number question. See here, this is a 41 number question. Okay, so let's just solve this question. Here, let's just assume n to be 2 power m, then t of 2 power m equal to t of 2 power m by 2 plus this is 2 power m square, right? Okay. So let's just assume that to be now Sm, this is S of m by 2 plus this is nothing but 2m, right? Now if you solve using the Master's theorem, can you tell me what will the answer? This is theta of it is m power something. It will ultimately with this only, right? Sm is this, which means you can say Tn is this. Now you put the value of m. So you can take the square both side and it will be n square only, right? It will be n square only. So you can say this is theta of n square. Very easily, see, very easily we solve it, right? Otherwise we have to do lot of struggle. Okay. Now let's just move to the next question. Let's just see this. Can you solve this question as an homework? Let me know. Or maybe we can quickly solve, right? Okay, these are 1, 2, 3. Okay. Can you okay? Do you want to solve these as an homework? I can okay, just solve that as an homework, and if the correct answer is there, I will reply whether it is correct or wrong. Okay, so just solve as an homework and comment for question number 42. Solve as an homework, okay, and comment for question number 43. Solve as an homework and comment for later on. Comment for question number 44 also. Okay. Now let's solve this question. Okay, this question has been asked in GATE 2006, right? So what they are saying that they want to solve this particular recurrence, right? Let's just solve this. So see here that what you can do, you can assume. Okay, let me put the options on the right side. So here you can assume t this n to be 2 power m because this is square root, so it is complex, right? So just assume it. So it will be t of 2 power m equal to 2 into t of 2 power m by 2 plus 1. And then what you can say is this is Sm, which will be equal to t 2 of Sm by 2 plus 1. Using the Master's theorem, you will get to know this is just theta of m, right? Sm is just theta of m, which means Sm is nothing but t of 2 power m, which is nothing but t of n, right? So which means you can say t of n is nothing but theta of m. M is log n, right? Very easily you can solve this. So what is the answer? B is the correct answer. Okay, very easily you can solve these kind of questions using the change of variable method. Okay, great. I hope you understood. Let's just solve this question. Okay, so basically we have covered change of variable method. Now there are some more tricky questions that we have, I think. Okay, there are some more tricky questions. Let's just try solving it. Can you try solving this as an homework and the answers? I mean, you just solve it. You don't need to comment the answers on the next page. Okay, answers on the next page. You can just check out. Okay, let's just see some more variations. Okay, so some more variations other than the change of variable. Okay, I mean the change of variable we have seen, but there could be some more variations which is very tricky. Okay, I mean not very tricky, but yeah, if you do not know, then it is little difficult to solve. So let's solve this. See, in this particular question, I have taken this question from Stanford. In this particular question, if you observe, then this is a power of the function itself, right? In that case, what you can do, if this is a power of function itself, then you can take the log. Okay, you can take the log. Okay, so here it is first you take the log. If this is power of function itself, then first you take the log. It is log of t n by 161. Okay, plus log n. Is this okay to everyone? I mean, these kind of things they have not asked in GATE, but by chance they ask. Okay, then first you take the log. Okay, then what you need to do, if by chance they ask, then if this is power of function, okay, power of function itself, you take the log, you make it normalize, okay, just normalize it, and then what you need to do, then you assume that to be Sn, okay, or maybe some, let's not introduce a new variable because I don't think we need it. Let's just assume that to be Gn. Okay, you don't need m here. So here it is g of n by 161 plus log n. You don't need m here. Okay, I'm directly working with n. Now you can solve this using Master's theorem, right? So if you solve this using Master's theorem, you will be getting, I think, n, because a and b are same. So I think you will be getting n. So this is theta of n. So you can say that Gn you have got as theta of n, right? So basically Gn is theta of n, which means Gn is nothing but log of Tn. So log of Tn is theta of n, which means Tn will be 2 power this theta of n, right? So maybe you can say 2 power theta of n, something like this. Okay. So basically, I mean, generally they won't ask you such type of questions, but even if they ask, now you know that how to solve, right? If the power is in the function itself, okay. So here again, the power is in the function itself. Let's just solve this question. So here you can assume that, okay, log n, I mean, first take the log. This will be log n plus 2 log of Tn by 2. Now what you need to do? Once you take the log, then you can assume that to be some function, right? Then you say that, okay, this will be, let's suppose Gn is nothing but 2 of Gn by 2 plus log n. Now this will be n, right? I mean, n power log base ba, so it will be n. So it is theta of n. So that's why Tn will be again 2 power theta of n. Okay, something like this. Okay, something like this. Don't worry. I mean, generally they won't ask if the power of function, but if that is the case, then you take the log first, okay, and then you solve it. Okay, cool. Now this is a question from MIT. Let's just try solving it. Okay, so this is again a question of change of variable only. So this is question number 49 that we are in. Okay, so let's just solve this question. This is a question from MIT, and this is change of variable. This is not a power of function or something. Okay, I mean, just a usual question. So let's just solve this. This question is from MIT. Okay, let's just see how we can solve this particular question. See here, this is given, right? Now what we can do here, if this kind of thing is given, right, what we can do here is that like earlier the difference between this question and earlier question is that earlier we were basically having, I mean, we were not having this multiplication, right? We were not having this multiplication. If I just recall you, see, earlier we were having 4 or something. We were not having square root as a multiplication, right? Square root of n as a multiplication. We were not having something like this. So now here I think this is the very first question where we have square root of n as multiplication. So in such case, what you can do, you divide by that. Okay, I mean, maybe you can divide by n. Okay, so basically here you can divide by n first. I mean, you do not need to remember. You will get to understand based on the question. Okay, that what we need to do. So here first we are dividing by n. Now let's just assume this to be Gn. Okay, you don't need any other variable. You can assume this to be Gn. This will be g of square root of n, right? Okay, or maybe what you can do, maybe you can assume the variable first and then you can assume that to be Gn. I mean, whatever you want, you can do it. Which means let's do one thing. Let's just do step by step. Let's just assume n to be 2 power m, n equal to 2 power m. So first you divide and then you are assuming this, right? So this will be t of 2 power m divided by 2 power m equal to t of 2 power m by 2 divided by 2 power m by 2 plus 100. Okay, so we have got this. Now what you can do, see, we have got this. What you can do now, you can assume this to be Gm. Okay, you can assume this to be Gm. So you will be getting Gm by 2 plus 100. Now can you tell me what is the answer? This will be just log m, right? So this is log m. So Gm is log m, which means this whole thing, right? The whole thing, which is basically t of 2 power m divided by 2 power m is log m, right? And now as we know that this is, I mean, this is nothing but Tn by n, because n is nothing but 2 power m, right? So this is, from here you can say Tn by n, and m is log n, so it is log of log n. So that's how you can solve Tn equal to n log of log n, right? Understood? So basically we have done it very simply. First we divided by n, and then we assumed, then from here on we applied it. Okay, if this is something like this square root of n, then you need to see some other trick. Okay, see, let's just solve this question, which is question number 50. Let's just solve this question. Here just divide by n first, plus 1, right? Now you can assume that to be 2 power m. Now you can assume that to be 2 power m divided by 2 power m equal to t of 2 power m by 2 divided by 2 power m by 2 plus 1. Let's just now further assume this to be g of m, right? Let's just now further assume this to be g of m, which is going to be g of m by 2 plus 1, which means this is just theta of log m, and this gm is nothing but Tn by n, right? So you can say Tn by n is theta of log n, and m is nothing but the same thing, log n, right? So it will be, Tn will be n into log of log n, right? No, we have not divided both sides by the different number. We have divided by n only. If you divide by n here, this will cancel out and this will be root n only. Okay, you n will get cancelled out. We are dividing by n only. We are not dividing by the different numbers. Okay, here also we are dividing by n. Here also we are dividing by n only. We are dividing by n, and then because of this square root of n, it is square root of n. Okay, we are not dividing by the different numbers. Understood? So basically, let me just repeat it. You divided by n, and then you are getting this, right? Then just apply the steps. Step 1, you put it like 2 power m, right? And then this is gm, the shorter form that you got, and then from here you can solve it, right? Okay. Now this is a question which has been asked in GATE. So this question is actually very, very tricky. In this question they are saying that we need to evaluate this Tn, right, to something. But here there is no theta, which means they are asking for the exact answer. See, in this question they are saying that give me the exact answer. They are not asking for the theta. Okay. So yeah. So here this is not theta. Okay, they are asking for the exact answer. So let me just solve it. See, Tn is given to be square root of 2 t of n by 2 plus square root of n, right? Okay. So maybe what you can do, maybe here, can you guess what you can do? I mean, you can directly assume n to be 2 power m. Maybe you can solve using that, but I think you can do little smarter thing also. Okay. So I mean, you can directly assume, but can you do something else? Let's just divide by square root of n both side. Okay, I mean, you can directly assume, but let me first divide by square root of n, and then it will be t of n by 2. This is square root of 2 divided by square root of n. This is plus 1. Then it is t of n by 2 divided by n by 2 square root, right? Okay, so actually it is coming a symmetric form, so that's why I was just saying that we can divide like this, right? Okay. Now you can do one thing. Now let's just do one thing. Maybe you can assume this to be some quantity. Maybe you can assume this to be some gn or something, right? If this is gn, then can you tell me, if this is gn, what is this number? What is going to be this number? This is going to be gn by 2. right? So we have got Gn equal to Gn by 2 plus 1, isn't it? Isn't it? But can you apply Master's theorem? Yes, but they are not interested in the Master's theorem. See, they are not asking for the theta. They are saying just give me the exact value, right? Just give me the exact value. So if you apply the Master's theorem, then what you will be getting? You will say this is log base b a, right? So this is 1, this is 1. I think you will be getting log n. This is just a binary search recurrence, right? You will be getting the log n. Now they are not asking for this. They are not saying that you solve this using Master's theorem, because they have not given the theta, and Master's theorem will give you the theta. So what you need to do? You need to solve this using the repeated substitution. Okay, you just solve this using the repeated substitution, and then you need to find the answer. So use a repeated substitution. See, the change of variable method is helping you, and then after that you need to use a repeated substitution. Right now, okay, so just try this question. What you need to do, you need to keep on substituting Gn by 2 square plus 1 plus 1 and so on, right? So you need to keep on doing it, and then finally find out the Gn, and based on that you need to find out this Tn. Okay, based on that you need to find out this Tn. Understood? See, if you want to find the value of G1, can you tell me the value of G1? It will be T1 upon 1, which is just 1, right? G1 is 1. So what you can do, let me just do it. See, we have got this, right? And the base case here is that G1 is 1. Actually G1 is T1 upon 1, so this is also 1. Okay, so let's just keep on doing it. See, Gn will be, if you do it one time, you will be getting G of n by 2 square plus 1 plus 1, right? So if it is 2 square, you are getting 2 times 1. Similarly, if this is n upon 2 power k, then you will be getting k times 1, right? K times, which is nothing but k. So let's assume that this particular quantity is 1. So it means this is G1 plus this is k, right? G1 plus k. Now this G1 is nothing but 1. So it is k plus 1. And what is the value of k? K, from here you can find out the value of k. It is n upon 2 power k is 1. So k is log n, log base 2n. So basically this is nothing but exact, I am telling you, this is nothing but log base 2n plus 1, not just log n. Okay, if you use a Master's theorem, you will be getting log n, but if you do repeated substitution, you will be getting log n plus 1, which is the exact value. See, this may not be the time complexity, or this may not be any other thing, right? This may be some mathematical recurrence that they want to solve, may not be just time complexity. So here we have got log n plus 1. So see here that Gn, we have got log n plus 1, right? This is exact. Is this theta? No, we don't need to use theta. We have found out the exact thing, and this Gn was Tn upon square root of n, and then they are asking the value of Tn, right? So Tn is nothing but square root of n into log n plus 1. So that is the answer, right? That is the answer. So see here, yeah, A is the correct answer, not B. Okay, because you need to add plus 1 here, because that's the exact thing that they are interested in. Okay, that's the exact thing they are interested in. This is very tricky, very nice question. I hope you understood it. Okay, most of the experience haven't understood this question. Okay, based on my experience, but I hope you understood this question now. What they are saying that you need to evaluate it. Okay, they are not using theta anywhere. They are not using theta anywhere. So that's why if you use the Master's theorem, plus 1 minus 1 might not be taken care. So that's why we need to use, okay, we can use a change of variable. It's not an issue. Okay, you can use a change of variable or whatever. I mean, from here itself, see, this is the given. If you don't click that, okay, you can divide by root n, don't worry, you can directly put n equal to 2 power m, and then you can solve it. But don't use a Master's theorem. Okay, that's what I'm saying. Don't use a Master's theorem, because they want an exact answer, not the theta. Okay. Now, can you solve this question? Can you solve this question? Okay. So there are multiple questions that are left to solve. So let's just solve this question. Okay. So I think there are 1, 2. Yeah. So there are multiple PYQs that we want to solve. let's just solve each of them one by one. Okay. Yeah. So can we have a break of 5 minutes? Let's just have a break of 5 minutes and then we will meet at 3:05 p.m. Okay. We will meet at 3:05 p.m. Okay. So let's just have a break and then we will solve all of the remaining questions. Yeah, hi everyone. So let us now start. Okay, so let us now start. Now we were saying that how to solve this question, right? This is question number 52. Okay, so we have solved many questions. Now this is question number 52. Let's just see how to solve this question. Now what they are saying that Tn is this, and then they want to ask that what is the final answer, right? Okay. So have we solved this question? I think we have solved this question, right? One question we have solved was that it. Yeah, gate 2006 question we have solved. Okay, I think this is different. Anyway, so let's just see this question, right? So what they are saying, this is the question that we have. They are saying Tn is this, right? Now how to solve this question? Maybe we can use directly Master's theorem, right? We can directly use Master's theorem. So it will be n, it will be root n. So is this polynomially greater? Yes. Since this is polynomially greater, so I don't think we do not need to not need to do anything. Directly you can say C is the correct answer, right? So C is the correct answer, right? Polynomially greater. Okay. Okay. Now tell me this. This is our test series question, and this is one of the very interesting question. Okay. Tell me this question. So what they are saying that Tn is 2Tn by 2 plus order of n. Okay. And then they are saying what will the asymptotic bound on Tn. Now see this question, in this question they are saying that Tn is this, right? In this question they are saying Tn is this. Now let's just see that how to solve this particular question. Okay. Let's just see how to solve this particular question. So here this Tn is basically 2Tn by 2 now plus order of n. This order of n can vary, right? That can be 1, that can be log n, that can be n also. So it can be this, I mean, or Tn can be this also, 2Tn by 2 plus log n, and or maybe plus n, right? It can be anything, right? Less than or equal to n, it can be anything. So this quantity is n's power log base ba, right? This quantity is n only, but this function can be 1. And if this quantity is n, this function can be n also. So in this case, what is the answer? In this case, the answer is log n, sorry, n log n. In this case, the answer is just n. So even if the function is n, then the answer is n log n. So which means that even if it is 1, then answer is n only. If it is n, then answer is n log n. So it will depend, right? If it is taking the highest value, then answer is n log n. So basically, is the answer n? Is the answer n? This is a MSQ question. Is the answer n? No. Tn is not n, right? Tn is basically you have seen it is n, right? See this Tn is, it is theta of n. It is also n log n, right? It depends on what value you are taking here, right? So you can say sometimes it is n, sometimes n log n. So at most it can be on n log n, because if you take this on n, so which means it is not theta. You can't write it as theta, right? It is not, I mean, for this particular general recurrence, you can't write it as any of the theta. So that is the reason, I mean, sometimes this is this theta, sometimes this is this theta. That is the reason all of the thetas are wrong. Okay, it is basically less than equal to n log n. It is less than equal to n log n. That's why it is order of n log n, right? Order of n log n. So that's why, since it is order of n log n, that's why it is order of n cube also. Okay, order of n cube also. Understood? So basically this is very interesting question. Students often get confused. They think that n log n both are the answer. No. Okay, so this order of n, this is the very first question where we have order of n in the Master's theorem. I mean, this instead of fn and fn directly, we have order of n. So now this order of n can range, right? So based on this you need to answer. Okay, this is little tricky, and here I have put order of n, and if you see, the answer is D only, right? There has been 38 upvotes on this particular question, on test series question. So generally, I mean, we don't get much upvotes on the test series question, because generally these are less exposed. So 38 upvotes on a test series question is basically extremely good. Okay, extremely good. Okay. Now let's see this question which has been asking GATE 2002. So what they are saying, what they're saying that what is this recurrence? So here they are not using theta or anything, right? Again, they are not using theta or anything. So that's why we need to be careful. Okay, we can't use the Masters theorem. We can use the change of variable method, but since they are not using theta or anything, so that's why we need to be careful. So let's just assume this 2 power k maybe to be m if you want, or maybe do you really want it, or maybe let's see. Okay, so 2 power k minus 1 will be m by 2. Okay, this is m3 of m by 2 plus 1. Okay, now if you solve this further, it will be 3 into 3 of t of m by 2 square plus 1, right? Okay, plus 1. So here I think it will be, you need to keep on solving it. Okay, so what is the answer? See, if you keep on solving it, you will be getting you can't use directly the Masters theorem and anything, because the thing is that they are not asking for the theta, right? They are not asking for the theta, so that is the reason. Okay, so it is 3 square into t of m upon 2 square plus 3 plus 1, right? I think if you keep on doing it, this will 3 power k t of you can say it will be t of m upon this is 2 power k, right? And there will be k such terms, so which means this is 3 power k minus 1 plus 3 power k minus 2 till 1. Okay, now let's just assume that to be 1, right? So basically k will be log n, so this k will be log base 2m. Okay, and what is this quantity? What will be this? 1 plus 3 square till 3 power k minus 1. What is this quantity? This will be, can you tell me the quantity? A into 1 minus r power n, or maybe r power n minus 1. So 3 power, how many terms are there? K, right? 3 power k, a into r power n minus 1 upon r minus 1, right? Okay, r power n minus 1 upon 3 minus 1. Okay, so this quantity is 3 power k minus 1 divided by 2, right? This quantity is 3 power k minus 1 divided by 2, and then we need to add this also. So basically you can say this tn t of m is nothing but 3 power k into t of this is anyway 1, right? Plus 3 power k minus 1 divided by 2. Basically this is 3 power k minus 1 divided by 2, right? Okay. And k is what? K is, from here you know, k is log base 2m. Okay, log base 2m. K is log base 2m. And t1 is given to be 1, so that's why it is 3 power k plus 3 power k minus 1 divided by 2. Okay, and this m is also we need to put. Okay, m we need to put, right? K we don't need to put actually. K is already in this, so k we don't need to put. We need to put m. M is 2 power k. Okay, so m is 2 power k. So t of 2 power k. So that's what they're asking, right? They're even asking, they're only asking t of 2 power k. Okay, they're asking t of 2 power k, which is going to be 3 power k plus 3 power k minus 1 divided by 2. 3 power k plus 3 power k minus 1 divided by 2. So what is the answer? Is anything matching from here? Okay, so let's just see. This is, can we take 3 power k minus 1 common? If you take 3 power k minus 1 common, then this will be 3 plus 1 by 2, right? So it is going to be 7 by 2. 3 power k minus 1 into 7 by 2. Okay, maybe we have done some calculation mistake. Let's just quickly check it. See, this is okay, this is okay. This is m by 2, that's fine. And then you need to write it t of m by 2, 3 into t of m by 2 square plus 1. Yeah, I think that is fine. This is going to be, okay, sorry. This is, where is that? Yeah. So this term is going to be a is 1, r power n minus 1 upon r is 3 minus 1. Yeah. Oh, this minus 1 is here. Okay. This minus 1 is actually not on the power. This minus 1 is here. Okay. So yeah, I think that is little mistake that we have done. Okay. So this minus 1 is not in the power. Right. So yeah. So you can say this minus 1, since this minus 1 is not in the power, so that's why. Let me write it like this. Okay. So what is the final answer? I think this is going to be, again, so this is 3 power k minus 3 power k plus 3 power k divided by 2 minus 1 by 2, right? Okay. Yeah. So this is basically uh, 2 into 3 power k plus 3 power k. So 3 into 3 power k divided by 2 minus 1 by 2. So I think B is the correct answer, right? B is the correct answer. So basically it was just a small typo that we did. Otherwise B is the correct answer. Okay. Cool. So see, in this question again, they are not asking for the theta. Okay, you need to be careful. Are they asking for the theta, or they are asking to directly solve? So if they are asking to directly solve, then you can't apply the Master's theorem. You can apply a change of variable or anything, but you can't apply directly shortcut like Master's theorem. Okay. Okay. Here they have applied the Master's theorem, but it seems that the answer is in the theta. See, if you apply the Master's theorem, then they are getting theta of 3 power k. Okay, then only one of the option is matching, then also it is fine. Okay, if only one of the option is matching, then also it's fine. Let's suppose one of the option is 3 power k only. Okay, one option is 3 power k only, then you can't apply the Master's theorem at least, right? So if only one of the option is matching, then yeah, that's okay. But in the earlier case, see, in this case, if we apply the Master's theorem, see, in this case, if we apply the Master's theorem, then we will be getting theta, right? Theta of this. So basically A and B both are in the same theta. So that's why the Master's theorem won't work here, right? Because A and B are both are the same theta, because theta of this we will be getting. Now here they have applied the theta. I mean, in the answer they have applied the theta, but fortunately, okay, fortunately only one of the option is matching. Now let's just see this. I think this is the question we have solved most probably, right? So now let's just solve this question, and then we will just wrap up. Okay, let's just solve this final question. So what they're saying, let's just see that Tn is this, where A and B are some parameters, and Tn is this, and Tb is given to be 1. Okay, can you solve this question? Let's just try solving it. Okay, so see here, let's just assume n to be 2 power m. So that's why it will be t of 2 power m equal to t of 2 power m by a plus 1, and then it will be s of m equal to s of m by a plus 1, isn't it? Let me know if that is fine to everyone. Okay, cool. So I hope that's okay. Now what will the next thing? Now can you apply the Master's theorem here? So see, they're asking in the theta terms, right? So you can definitely apply the Master's theorem here. So what is the n power log base b? What is the b here? So a is 1, b is a, right? Log base a and 1, which is just 0. So that's why it is 1. So log m is the answer here, right? So you can say here the log m will be the answer. So this is nothing but theta of log m. Okay, and then you can solve from here, right? so the base case they have given us TB. Okay, that's quite interesting. So here in the Masters theorem, if we apply, then I think the base case is actually taken to be T1, right? The base case is taken to be T1. So, but here the base case is actually given to be TB. Okay, something else is given to be the base case. See, something else is given to be the base case. So if we apply the Masters theorem, then also we get the answer. But the base case here there we assumed to be T1, but here the TB is given to be the base case. So maybe what we can do, we can apply any other method. Maybe you can just do the repeated substitution, okay, and then assume that okay we will stop at TB. Okay, so let's just apply the repeated substitution. Now it will be s of m by a square plus 1, and then if you keep on doing it, s of, so it is s of m by a power k plus it is square then 2, then it is k, right? Okay, understood. Now we want to stop at TB equal to 1, right? So if TB is 1, which means then at what value of s we will be stopping? Can you tell me? See, let's just assume that Sm we are getting this. Okay, Sm we are getting this, right? Now we want to solve for T. We don't want to solve for obviously S and these things. So let's just do one thing. Maybe we can do one thing. Maybe see, we want to find out the value of K, right? So here it is actually very tricky, it seems like. So here let's just substitute this T back. Okay, let's just substitute this T back. Now if you substitute this T back, Sm is nothing but T of 2 power m. Then what will be this value? This will be T of 2 power m divided by a power k, right? This will be something like this. See, this will be T of 2 power divided by a power k. Let me know if you are getting it. Okay, plus k. Let me know if you are getting it or there is any issue in understanding this. See, what we are doing is basically we are first having the change of variable and then we are doing this, right? Is this okay? Okay, so now let's just solve this. So basically now we want to stop at b, right? So basically you can say this is nothing but b. Okay, this is nothing but b, which means 2 power m upon a power k is nothing but b, right? So from here can you calculate the value of k? So m upon a power k is nothing but log base 2b, and then k will be, see, m upon a power k is log base 2b. So from here you can say a power k is m upon log base 2b. So k will be log base a m upon log base 2b. Okay, this is going to be the k, right? Let me know if that is okay. See, this k will be, a power k will be m upon log base 2b. A power k will be m upon log base 2b, right? Now we are interested in the value of k. So the k will be this. Okay, now from here we know that this recurrence, right? This recurrence that we want to solve. So see, this 2 power m is nothing but n, right? So this is T of n, this is T of b plus k, right? So T of b is 1. So this is 1 plus the k only, right? So what is the k? K is log base a m, and what is the value of m? M is log n, right? So basically this is nothing but log base a log base 2n upon log base 2b. Do you remember one property? Using which you can also write it log base bn, this particular term, right? Log base bn, if these two log are same, then you can write it log base bn. So basically you can say k is nothing but log base a log base a, k is nothing but, see here, k is nothing but log base a into, inside this log base b n, right? Log base a, log base b n. So it is log base a, log base b n. So which is theta of log base a, log base b n. Okay. Yeah. So what is the correct answer here? A is the correct answer, right? Log base a, log base b n. Okay. There are some tricky questions that they have asked. So we have solved all the questions. So total 56 questions we have solved in this session, right? I hope you have loved this session. If you have loved this session, then just let me know. Okay, just let me know that that you have really liked this session. So see, A is the answer here, right? So in this session, we have covered all type of recurrence. Okay, type of recurrence question. Just comment it out. Okay, just comment it out. Okay, so please comment if you have liked this session, if you have loved this session, just comment it out. Okay, just comment it out if you have loved this session. Okay, so that is all about all type of recurrence relations, right? All type of recurrence relation. Just let me know how you like the session so that we can bring more such sessions. Okay, so that we can bring more such session. That is all for this particular session. We will be bringing more such sessions, but for that you just need to comment it out. Okay, if you have loved it or if you have not loved it. Okay, just let me know. I hope you really like the session. So I will just request you to put a comment here so that we get motivated. Okay, so just please put a comment, and then we will be conducting more such revision sessions. Okay, so thank you everyone. Take care. Bye bye. So just comment it out later on the video. Okay, not on the live chat. Later on the video, just comment it out.